we can kind of start here. Hi, everybody. Hope you're doing well. Hopefully you'll be doing well after 10 o'clock tomorrow. So yeah, it's less than 24 hours. We'll be done with this whole thing. That'll be it. So let's keep going here. So today we have 3 hours. If you want to stick around for that long, feel free to. We're going to kind of just go through as many problems as you want and as many topics you want. I have my whiteboard here. We have, I have all the files. I can pull up WebAssign. I can do all of that stuff. And again, this is all going to be independent of last 2 review sessions. So if you want to ask questions again, or I get a repeat question, it's absolutely okay. The more we talk about it, the better. So we'll be happy to do about that. If you have a question that you want to tackle or want me to clarify anything, feel free to either unmute yourself or post in the chat or something like that. And yeah, I think that's basically it here. So I guess, does anybody want to start off with any questions of their own that they have here?
I have a quick question. It's regarding integrals. Can you tell me the difference between the integral of f of r of t times the magnitude of r prime of t versus the integral of f of r of t just multiplied by r prime of t and not the magnitude?
Do you mean the physical difference, or why we have to do that individually? Do you get my question there? Do you want to know why we have to do it that way, or like what the physical meaning is?
Do you mind both, actually?
Totally okay. I can do both. So let me first off, hold on 1 second. Can everybody see this whiteboard? I think we can. So wherever this is. Oh my gosh, I did not start my, hold on 1 second. I just realized my Apple Pen is not connected. Give me 1 second.
Nick, do you know how many questions are on the test tomorrow?
Since he said 12 pieces of paper, I'm gonna go with 12.
Okay.
That's my assumption. I do not know. I do not know more specifically here.
Okay, thanks.
I will unfortunately find out at the same exact time as you. Actually, I don't know that if that's actually the answer, but I'm pretty sure it's probably 12. That's my guess. So you were asking, I think that was Kayla that was asking that question. You were asking the difference between why we have to go between this, basically between these 2 things here. And so let's first off talk about the differences between these 2 kind of integrals here, and then kind of work from there and work from that. So here, the first one here is I have a curve C, and I'm moving via a vector field. So this is kind of a work integral here. And what is this really saying? I kind of want to just point out, what does this dot dr really mean, right? This dot dr is really saying it's the force vector, the force vector field dotted with the tangent vector. Actually ds, like this. Sorry, lowercase s here. I should kind of realize that. So this is actually the force field dotted with the tangent vector of my curve, specifically. And so, you know, when I have this dot product here, well, how else can I write the tangent vector? You want to kind of remember that, right? How else can I write the tangent vector? Well, if I think about the unit tangent vector as reminding of our T and B frame kind of thing, we can kind of say that the tangent vector here can be written as the derivative of my parameterization divided by the magnitude of my parameterization. As a reminder, we have this ds here, this arc length, which we know is related actually to the magnitude, right? We say that ds is equal to a magnitude of r prime of t dt. And so kind of combining these 2 things and kind of working this all out, right, we can actually see that this is from A to B. The vector field at the parameterization of r of t, dot product with my tangent vector, the r magnitude of r prime of t dt. And we see that these 2 things cancel. So we do have as our final formula, if we're just kind of doing this without any basic rules, if kind of our theorems and stuff, this is kind of how we would evaluate this. So think about it this way here. So if I have a dot product here, I need to integrate this from A to B, right? I'm going to need to parameterize this. I can't integrate a vector field. It would make no sense for me to do that. It really wouldn't. So in order to kind of work with that, I need to take a dot product to get a scalar value out of it so I can integrate them. And so that's kind of how we kind of think about this. This is the vector field dotted with the tangent vector. Kind of the same exact way that we think about work, right? This is kind of a work, and we kind of integrate over my entire curve. In this capacity here, well, we're kind of saying this is a little bit tougher to come up with a physical representation of this, or you might have just f of x, y. We can even think about it this way, x, y, ds, but it's the same exact idea. And what we do instead, again, is I replace my my function here, my scalar function, with r of t. But again, this is something like, it could be maybe as an example, like x squared plus y squared. It would make no sense for me to multiply this by a vector or take a dot product, because this is a scalar function. So it really wouldn't make sense there. So again, I have this function now. I plug it in as r of t, and now I want to multiply it by something. Well, as a reminder, ds here, right, is the magnitude of r prime of t dt. dt like that. So that's kind of how we get this. And you kind of think about this integral if you're trying to worry about this. This is the area under my curtain, my net area under my curtain. So I have my curve C. Kind of, if I visualize this very quickly, my curve C is here. Maybe my function is something up here, right? I can actually take this curtain and calculate at every single point there, and it's the area of this curtain, kind of like that, where my curve C is down here. Try to do that. If it was f of x, y is z, it would be maybe like a mass. It would kind of be a density there. But it's the same exact procedure, kind of working with that. So this is is a work integral. The second part is more of a density or an area integral here. And the reason why we need to take the dot product in the first one is I need to get this to be a scalar value. Right? So I need to take this a dot product to kind of expand it. And it's based off with the tangent vectors, right? The tangent vector is r prime of c over magnitude of r prime of c. So I need to take the dot product of that specifically. But here, I don't do that. I actually, ds here, all I'm exchanging is this differential, this arc length differential. And I'm just exchanging that for the magnitude of r prime of t dt. Is that kind of the question you were asking there?
Yeah, thank you.
Yeah, no problem. Anybody have any questions on that specifically here?
So I actually do have a quick question. I guess maybe because this is a double integral, but there was a formula sheet that's a double integral surface f of x, y, z ds equals the double integral of f of r of and it uses the cross product.
Yeah. So that's related to that's actually different than this. So this is actually, so you're thinking about this guy specifically, where this here is a kind of a difference there. So this, I'm integrating over a curve, right? I'm integrating over a curve here. And so I'm only considering my parameterization of my curve, which is r of t. In this case, what I do is I have my surface here. I have a complete surface. And what I want to do is whenever I kind of work with this, I need to first off figure out, well, what's my parameterization? So we usually parameterize it as r of uv, where uv is in some domain d, right? You could use r and theta, x and y, whatever it is here. And now how do I replace this dx, right? How do I kind of replace this? Up here, what we did is we took the magnitude of r prime of t, right? So we took the magnitude of the derivative. Now, I hope you'd agree, I can't really say take the derivative here. I have to be very specific about what derivative I'm taking. So the derivative I'm taking, I have to do RU or RV, but in this case, I have to do both. And why is that? Well, as a reminder, this is a surface differential. So I can actually use the same exact picture here, kind of imagining what I'm doing. I'm taking my surface and I'm kind of, making it look like a steak, for instance, here, but I'm kind of partitioning it. And I'm kind of looking at each one of these individual areas. And I'm trying to add up all the contributions here. So this differential here, this ds, is related to this area of this box. Every single one of these parallelograms, actually. Here. So how do I come up with the area of that? Well, as a reminder, if I have two vectors, A and B, and I want to come up with the area of this parallelogram that they're formed, how do I do that? Well, as a reminder, if kind of thinking about this area here, we kind of use this theta. Right? This is the magnitude of A times sine of theta, right? Because of the cross. and this is the magnitude of B. So you can kind of think the area of this parallelogram here maybe is the magnitude of B times the magnitude of A times sine of theta, which if you're wondering, is just the magnitude of the cross product. And so you can calculate the magnitude of the cross product between the vectors A and B and get an area of a parallelogram. And so what I'm basically doing, and why am I talking about this, right? What is the point of me talking about this whole tangent here? Is that I have a point. I'm going to use a completely different color than that. I have my, I picked a different color. Thank you. My point like this. Let's say I'm trying to do this. Well, I have RU is maybe in this direction, and RV is in this direction. These are the level curves. This is actually how I'm parameterizing my surface here, kind of like that. And in this case, right, what I'm doing here is I'm basically trying to find the area of this parallelogram in this case. So in order to do that, I can basically just calculate as RU cross RV and the magnitude of it. So basically what I'm doing is I'm calculating RU cross RV at every single one of these points in here. I'm calculating the infinitesimal areas. And so we can find that to exchange this, df is actually equal to, sorry, df here, the differential, is equal to the magnitude of RU cross RV dA. And so that's why when I replace this integral then, if I can now zoom out, sorry, this becomes the double integral over my domain D because I've parameterized. I replace my function as R of uv, and I have to multiply it by the magnitude. It wouldn't make sense for me to do RU cross RV because that's the normal vector, right? RU cross RV is a normal vector. I have a scalar function here, so I can't do that. So what I have to do is I have to do the magnitude of RU cross RV dA. And similarly, why don't we just keep going on this trajectory while I'm there? If we have some integral like this, a flux integral, again, what does this really say? Well, this is saying I'm taking the flux, I'm taking the vector field and dotting it with, taking a dot product with the normal vector of my surface, where this is a big X. What is the normal vector of my surface? Normal vector of my surface is RU cross RV. And so that's why this whole thing becomes, well, I plug in my parameterization to my vector field, and then I take the dot product of RU cross RV with it. And again, in the same exact manner, right, I have a vector field, so I have to take a dot product because I need to make this a scalar. In a similar way, I have a vector field here. I need to take a dot product because I need a scalar function to evaluate that. And so that's kind of the differences between these four things. You would never just kind of working through this. If you're ever asked for flux, right, you would automatically use this integral, right? This is a flux, always. If you hear the word flux, you're calculating this type of integral or this type of integral. It's the same thing. If you're asked for the amount of work, you calculate this integral. You'll say either the amount of work kind of going in that case, if you're asked to do that, kind of prompted. Otherwise, you will not be really able to, they would tell you just evaluate this, or they would tell you just evaluate this. Those are a little bit more complicated with application-based things, so we really want to go there. But if this is work, you use this integral. If you use flux, you use this integral. Depending on how you want to go about computing it, well, that's dependent on a couple of factors, as we've kind of discussed before. But this is how you would do it with parameterization. Does that make sense? Did I answer your question there?
Yeah, you did, and that does make sense. Thank you.
Great, no problem. I'm happy I did. I sometimes go off in these weird tangents that kind of make sure, but I just want to make sure that I answered your question there. This is all really good stuff we got to go over here. Kind of think about that.
I have a quick question about that then. So when would you use the integral that's written in dark blue if the one below is for flux?
This one?
Yeah.
Only if you're given an integral like this.
Okay.
There's not really a like it would honestly, and this is just something like there's no real application that we can tell you that this is from. You would just be told, yeah, like you would say, like a question would be something like compute. They would say like compute x z ds, where f is some surface of like the cone, or something like that. They would tell you that. They would say compute this. They wouldn't go compute the density of it. They wouldn't do that. No, they would actually give you that. Yeah.
Okay, thank you.
Yeah. so this is again the kind of referring. Yeah, I'm getting some questions about this specifically here again. So again, if I get work, if you see the work integral, this is this one. This one, you would always be prompted with whatever this is. You would never be asked to say, oh, what is the area of the curtain in that case, and come up with that integral yourself. But this is the area of the curtain. Kind of as a curtain here, as I've kind of described in this guy, right? That's the area of this. You would just honestly just be asked to kind of just compute this integral. Similarly with this guy, you would just be asked to compute this integral. This is always.
I have a question. So for the top two, are they like the 2D versions of the bottom two? Is that what you're doing? Because you did like f of x, y, and then that is like the same as the f of x, y.
They're kind of the 2D. They're the kind of the two-dimensional versions, right? They are kind of that. I just want to be careful with how I say this. So this is over curves. These are over surfaces.
Okay.
That's the main difference. You kind of evaluate them in a very similar way, as I hope you can see. Or you kind of evaluate them in a very similar way. But this is only for curves. These also work in 3 dimensions, right? If I have a 3-dimensional curve, this is totally okay as well. It's the same exact idea. This is only for surfaces.
And we'll be told whether it's like a curve or a surface, so we know which one to use.
Yeah, you would definitely be implied that. You either say, like they would say, where C is the curve, or where S is the surface, or the intersection of these two things, which is going to be a curve or something like that.
Okay.
Yeah.
Thanks.
Yep, no problem. Okay, does anybody have any questions here just specifically about this?
Is that where it says flux? Is that supposed to be an f double integral of f ds?
This is f dot ds. Yes.
Okay.
Yep. It's f dot n. As n is the unit normal vector. This is actually the unit normal. What's it called? The unit normal. Yeah, I apologize. My f start to look somewhat. I don't know why they were like, oh, I want to make it look like the letter p. Sorry, and we'll kind of do that there. Yeah. So this is the vector field f always. Yep. We called it the unit normal. Okay. So if without further ado, then I do have another. I have a question about spring 2018 number 3 from a couple people actually, not just one. So I'm going to go do that one next. Unless there's anybody have any just general questions about this here, because this is like the whole ball game.
I have just a quick question on the yellow at the bottom. So if the flux is the f dot ds, how can it also be f dot n times ds?
This is just a simplification. This is just notation, the same exact thing as this.
Okay, but it's expressing the same idea.
Same exact idea. Yep.
Okay, and like when they give you the f, it's probably already in terms of, being dotted with the normal, right?
Say that again?
When they give you, like in the question, the f, it's probably already in the left form, the form on the left.
Yeah, so they'll usually say, evaluate this integral where f is blah. But this is, again, the exact same. These are both the exact same thing. This is just notationally how sometimes people write it. The same exact way of this is the same exact thing as notationally what this is. It's just a different way of expressing it. These are the exact same thing. So you could, if you're given this, it's the same exact thing as evaluating this.
Okay, that makes sense.
Yep. Mathematicians sometimes just like this. That's actually those are physics people. Those are physics people, not math people doing that. So see physics people. I probably shouldn't do that. That's that. Okay, so with that in mind, then I am going to go into spring 2018 number 3 here, which I'm assuming is about the curl and the divergence one. I think that's kind of what some people are asking there. So I'm going to do that. So spring 2018 number 3. And so this is the vector field. The vector field f, x, y, and z here, which is equal to the vector field x, y, and x squared plus y squared. Okay, so I'm going to move over this way. If I may, because I'm going to need, I think, a lot of space for this problem. So the first thing that is asked in this problem is to compute the curl. Now, why do we need a curl, right? What does this really mean? The first thing to realize is that, if I just have a vector field that's just PQ, right? If I just have a two-dimensional vector field, and I'm just trying to, come up with some, I want to find if this is conservative or not, right? Conservative means that there's an equal sign. It's equal to the gradient of some potential function. So how do I do that, right? I use Stokes theorem in some way, right? And I kind of utilize that. I say Py is equal to Qx, and this means that vector field is conservative as this happens. Now, in a three-dimensional sense, right, we have actually a lot of different choices here. In a three-dimensional sense, if I want to see if a vector field is conservative or not, I have to make sure that all the second derivatives are equal. So phi xz is equal to phi zx, and phi xy is equal to, and all those things, right? Making sure that's all are calculated. And the way you can do that, very simple way, is to calculate the curl of a vector field. The curl of a vector field is evaluated sometimes, oh, whoopsie, sorry. Oh no, sorry about that. Hold on 1 second. I actually went back out of the page. I couldn't start writing. There we go. Ijk, ddx, ddy, and dz, p, q, and r. Something like this. You sometimes see this as the gradient cross f here. You sometimes see something like notation like this, which is actually very common. So to compute this, what we do is we compute the curl of f, and I'm going to write this. I usually just write it always like this here. I don't memorize or remember how to do it as it's simplified, so I'm just going to write it like this. You put x, y, and z here, x, y, and x squared plus y squared. And we go ahead and try to compute this. The curl is going to be a vector. It's going to be a vector field itself. The curl of a vector field is a vector field itself. It discusses the rotation. So again, if I tell you the curl at a place, it is actually the axis on which an object, if you place it in it, would rotate. So curl kind of revolves around rotation here. If the curl of f is 0, you can actually find that this vector field is conservative. 0, the vector 0, because that means it's irrotational. That's kind of what we say. So in this case, my I component is going to be this derivative with respect to y, which is just 2y, minus this derivative with respect to y, with respect to z, which is just 0, because there's no z component there. The j component here is going to be this derivative with respect to x, with respect to z, sorry, which is just 0, minus this derivative with respect to x, which is 2x. And lastly, the k component is this with respect to x, which is 0, and this is also 0. So this is 2y, negative 2x, and 0. Okay, that's the curl. So this curl, we kind of see that we only rotate in the xy plane. Actually, in the that is, we rotate in an axis that is parallel to the xy plane. It's kind of interesting there, because there's no z component. So again, if I don't know if this is going to be on the exam, which I don't think it will be, because you guys really cover it. But at least just to let you know, if the curl of f is equal to 0 vector, f is conservative. That's just an important point to know, just usually. Here, the next thing we kind of tackle is the divergence of f. We sometimes consider it as the dot product of the gradient vector of this. If the k component is 0, no, that actually doesn't really signify anything, but you kind of see that if I kind of wrote this out more formally here, you'll notice that in the z component, I get qx minus py, which is very similar to my conservativity argument from here. So it's not really an important aspect of it. It just means that in 2 dimensions, it would be kind of conservative in that case if I kind of just ignored it. In this case, right, what we do is we calculate this. We take the derivative of each component with respect to its variable that it means. So we do px plus qy plus rz. So we take the derivative of the first component with respect to x, second component with respect to y, third component with respect to z, and we add them together. Or more formally, this would be x, y, and this would be x squared plus y squared, which if you notice here, this is just 1, this is just 1, and this is just 0, which is equal to 2. Okay, so I have my divergence here. Divergence, if you're wondering, kind of an important fact, I think that some people have already taken. The divergence is a number. A divergence will give you a number. It will give you a scalar. Oh, sorry, it will give you a scalar function. It could be just a function. It doesn't have to be a number. Curl will always give you a vector. What does the divergence actually mean? Well, it tells you how divergent the field is at a specific point. So the divergence is greater than 0 at some point. That means more water, if you consider F to be like a water, kind of like a fluid, it means that more objects are moving away from that point rather than coming in. We call this a source. So you can kind of imagine, like, I don't know, a dam. For instance, more stuff is going out rather than coming in here. So that'd be a source. If the divergence is negative, that means that more stuff is coming in rather than going out. We call this a sink. And if it's 0, we call this irrotational or divergence free, which means that the same amount irrotational. Sorry, not irrotational, sorry. Incompressible, my gosh. It's called incompressible. So incompressible basically means that the fluid moving into a point is the same moving out of a point. Water, for instance, is incompressible. However, some other fluids and liquids are not. For instance, air around an airfoil, like a kind of a wing of a plane is not. Also, ketchup isn't. Related to Newtonian fluids. Regardless, that's not really important. The important thing is at least to know the significance of these kinds of things here. Okay, so now the last thing here, and the lengthy part of this problem, is to use the divergence theorem to compute the flux of the integral across the hemisphere. X squared plus y squared plus z squared is equal to 9, where z is greater than or equal to 0. I want to compute the, here I want to compute specifically the flux across it. So again, we are computing this integral here, okay? Now, if we are computing this integral here, I want to be very, very careful. So it says to use the divergence theorem. So what does the divergence theorem say? Let's just kind of review that. So this is a really important point before we go forward. So in this case, what does the divergence theorem say? Divergence theorem say. So let F be some surface that completely encloses. It encloses a volume. I'll name it E. So imagine, for instance, that I say that, and this is a really, really important point here, that if I am taking this cylinder, let's say this water bottle here, I consider the surface every part of it. It needs to incorporate, it needs to encapsulate all parts of the surface, because I need to be bounding specifically the volume inside. Okay, I need to be completely bounded. If it's not completely bounded, I either have to work with something else, or I have to try to manipulate the function in some way, manipulate the surface in some way to kind of get that. So it has to completely enclose a volume. And we always consider, this is really important, we always consider the outward normal. Outward normal vector. What do we mean by the outward normal vector? S has to be oriented so that the normal vectors are always pointing outside of the volume. So what do I mean by that? There's always two normal vectors, right? There's always two normal vectors I consider. One is going out, one is going in. I want to be considered always the outward normal. Okay. If you do consider the inward normal and you want to use the divergence theorem, you put a negative out in front and everything's kind of kosher. So if I do this, then this integral, this flux integral, it's not really that many conditions, which is kind of nice here. If it completely encloses the volume, I can calculate this instead of going through that whole process of parameterization and all of that. What I could do is I could just evaluate this as the triple integral over my volume E of the divergence of F as my scalar function that's inside of here, dV. And this right here is my big theorem. This is the divergence theorem, which says I can calculate the amount of flux that goes through a surface. How much fluid is moving through my object is related to the divergence, which we kind of saw was kind of related to how divergent the vector field is inside of my solid. that's kind of bounded by it. So the big important thing to realize is we need to have a surface that completely encloses a volume. So with that in mind, why am I being very, very hasty about that? Well, in this case, I'm going to now tackle this problem here where I want to just compute just on the hemisphere, just on the top hemisphere. So let me kind of draw this out. Let me be very, very clear here. So I have X, Y, and Z. This is a sphere of radius 3. And I'm just considering the sphere of radius 3 on the top part. Okay. Like this. Okay, so I'm considering this surface now. Now, I am just considering, and this is really important, it just says to compute the flux across the hemisphere. Just across the hemisphere, which is just this guy on top. Right? It is just, imagine this as I kind of reframe this. Imagine this as a Tupperware. Okay, that's flipped over. The potato salad's gone. Right? If I just have a Tupperware on the top, I have this bowl. Okay, I have this Tupperware. I am just trying to calculate the flux on this Tupperware here. So now it tells me I want to use the divergence theorem. If I want to use the divergence theorem, I need to completely enclose a solid. Currently, I don't have that. I am just talking about the across the hemisphere here. So in this case, I do not have this bottom part. I don't have the lid to the Tupperware. I need the lid to the Tupperware before I can actually use the divergence theorem because I need to be completely enclosed in it. So if I include both of those, then I could use the divergence theorem. So let's kind of work this through and kind of see how this might work. So I hope you'd agree there's two surfaces. The first one is this S1 up here. I'm actually going to use green because I just did that. I should not use that. S1, okay? Then on the lid here, I'm going to call S2, which is just on my XY plane, okay? So this is my lid down here, S2 here, okay? Now, I am asking here, especially if I'm trying to come up with this, my surface here, my complete surface, is equal to S1 and S2. We use this union symbol to denote it's a combination of both S1 and S2. If I use this, then I could use the divergence theorem. So thinking about this, if I calculate the flux on the top and the flux on this lid, what I can then do is I can calculate that, and that's equivalent to the divergence theorem. So I can use this E here, which is the volume inside of my hemisphere. Okay, so let me write this out more formally here. If I want to use the divergence theorem, what I have to do is I just say, okay, well, I'm going to calculate the flux across that top part. I'm going to add it to the flux I calculate on the second part, on the lid. If I do this then, well, I have this full thing now on my left-hand side, and then I can utilize E here, and E is the upper half of this hemisphere. By using the divergence theorem, I can then evaluate this here, like that. And so again, all I'm trying to calculate is this integral right here. My goal is to calculate this. I'm just trying to tackle this upper half of this hemisphere. I'm trying to calculate these S1 here. So in order to do that, I'm going to subtract this over. And I hope you'd see that to evaluate this integral, S1 f dot ds. Yeah, my f's do get really, really close to p's, and I'm sorry about that. I need to calculate the triple integral here, dv, minus the flux through my bottom portion here. Okay? Like that. And now this is what I have to calculate. So I have to do two things. One, calculate the volume integral of div f in this volume here, this volume specifically from this half of the hemisphere. Secondly, I have to subtract that from the amount of fluid that's moving through the lid portion. We do two different things here. So I'm going to just really pause for a second and to see if anybody has any questions about where I'm going from here. I hope that makes sense. But if you have any questions or ask any questions, let me know right now before I continue moving through and evaluating both of these.
So because they say that it's that it's across the hemisphere, that's why you don't include the lid, correct?
Correct.
Okay.
Right? Because as I kind of, I think I said this yesterday, but just as I thought of this kind of a weird analogy of it. Like if I told you the northern hemisphere, you wouldn't count everything inside of the Earth.
Yeah.
Of the northern hemisphere, right? You would count just the outside of it. That's kind of what we're talking about here.
Okay.
Yeah. Yeah. Oh, I have a little world here. We could even think about that. But yes, I hope that, does anybody else have any questions, at least on this part? Because I'm going to continue doing this problem because there's still some really interesting things, especially with S2 here, to calculate that. If you do, feel free to put it in the chat or yell at me. Either one is okay. So I'm going to calculate both of these. So the first one, I'm gonna call this 1. I'm gonna call this 2. Let's do both of them. 1 is actually very quick, which is really nice. 1 here, well, this will evaluate pretty nicely because I know the divergence of my vector field F I've already calculated here, it's 2. And so in this case, it's really nice that this is actually, as a reminder, if there's a 1 in here, if I just have a 1, this is just equal to the volume of E. And this is a really, really, really handy tool. Similarly, if I have the double integral of a 1 dA, this is equal to the area of my domain D, for instance. These are two really, really, really important things to really quicken a lot of your calculations, especially on these kinds of examples. You have a 1 here, you have a 1 here. This is the area of your domain. If it's a double integral, it's the volume of your domain. If it's a triple integral, many times it's very easy to calculate. So here, this is just 2 times the volume of E. Now, the volume of E here is just half of a hemisphere. So I can calculate that really nicely. Oh, sorry. So as a reminder, what I could do here is the volume of a full sphere is 4/3 pi r to the third. And I'll just divide that by 2. So I can kind of, right, because it's just half of it. So it would be 2/3 pi r to the third. In this case, r is equal to 3, which is then going to be here, lastly, 2 times 2/3 pi to the 3 halves, to 3 to the third, which is just going to be 36 pi. That's this first part. Really quick, really nice, not too bad at all. The second part, a little more tricky, but no issues. We can do this too. So now I'm trying to calculate F dot ds here, where S2 is this bottom surface. So I'm going to this time go through the full parameterization here. If you don't know this, let's just work through it. Let's just go through the whole process here and not worry about that. So the first thing we do to try to evaluate this, right? We want to use this formula here. I want to parameterize my surface, and then I want to calculate my normal vector RU cross RV, something like that here. So how can I parameterize this bottom surface? Well, if I give you 2 variables, could you give me the third, right? If I want to try to find 2 variables that can explore this entire thing. Well, as a reminder, what does this look like? If I want to draw this, I hope you agree that S2 actually lies completely on the XY plane. And it's a circle of radius 3, like that. So what's nice is, I hope you'd agree, Z is 0 here, right? On this entire surface, Z is 0. So I could come up with a parameterization in terms of X and Y, which is just X, Y, and 0. It's just, I'm honestly just, because think about what I'm doing. I'm parameterizing just the XY plane. In the XY plane, I know Z is 0. That's the plane I'm parameterizing. And so I know Z is 0. And so now all I worry about is what X and Y are, right? What are the bounds? Well, X and Y are the bounds here, in this here. Now, I hope you'd agree that this is probably going to be a little bit better using polar coordinates or cylindrical coordinates kind of to mimic this here. So what I could do instead is say, all right, well, what if I just instead did r and theta, which is r cosine of theta, r sine of theta, and 0. That's not too bad. And then I tell you that my radius would be between 0 and 3, and my theta would be between 0 and 2 pi. And so this is a parameterization I could definitely use to kind of go forward here. That's pretty nice. So now going forward, what do I have to do? Kind of working back here, I see that I have to compute my normal vector, which is RU cross RV. So let me do that. In this case, RR cross R theta. I'm going to move up here to do that. RR is going to be cosine of theta, sine of theta, and 0. R sub theta here is going to be negative R sine of theta, R cosine of theta, and 0. And so if I want to calculate my normal vector, which I have to, we should kind of imagine that this normal vector should be pointing directly down. I hope you'd agree. This should be pointing directly down because I need to be an outward normal. So it should look like 0, 0, some number, right? 0, 0, some number could work. Cosine of theta, sine of theta, and 0. It can be negative sine of theta, or cosine of theta, and 0. And so we can come up with this here. My I component is going to be 0. My j component is also going to be 0. And my k component, oh, how about that? It's going to be r cosine squared. That's going to be plus, say, plus r sine squared of theta. So I hope you'd agree is 0, 0, r. So it's just in the z direction. Now, this is a really important point to make here. To use the divergence theorem, this is really important. I must have an outward normal, which means that my normal vector must be pointing outside, out of my volume here. I hope you'd agree that this vector field for all r is pointing directly upwards at the moment. Right? It's pointing upwards. I can't use that. I have to go the exact opposite way. I want this to be downward because I want this to be out of my domain. So all we do instead, and this is honestly what you could do instead, you can go, oh, okay, well, I'm going to change this then to 0, 0, negative r. I'm going to negate everything. And from that point, we now have the correct normal vector to use here. Okay, and this is the normal vector that I'm now going to use going forward. You always need to check that because for divergence theorem, you always need the outward normal. Okay, so with that in mind then, we can then try to calculate this, which is going to be the double integral f dot dr, sorry, dx, here, this parameterization. So again, what I'm going to do is I have to calculate for my domain D, f of r theta, dot product with r sub r cross r sub theta. Okay. And we see here, I have to plug in this parameterization right here into my vector field, which we've forgotten about already. Sorry, our vector field is x, y, x squared plus y squared. So I'm going to get r cosine of theta, r sine of theta, and then r cosine squared plus r sine squared, which is going to just be r squared. So as a reminder, we're going to get something like r cosine of theta, r sine of theta, r squared, dotted with 0, 0, negative r, dr, d theta. Because now it could actually come up with my bounds for this, which is 0 to 3 and 0 to 2 pi. In this case, I would go from 0 to 2 pi and 0 to 3. The dot product here is actually just always going to be 0. In this case, for the first two, the last one is going to be negative r to the third dr d theta. And from here, I can integrate this out. And then what I do to kind of end it, here, where I would just integrate this out. Once I get that answer, I would take this number and subtract it from this number, whatever I get here. And that's my answer. The other way you could have done this, if you noticed, maybe a little bit more formally, if you liked it this way instead, you can absolutely just keep doing it this way. This is totally fine. The other way you could have done it is to note that your normal vector here is really, really simple because as I kind of had thought about, right, this is the same thing as S2 F dot n here, dx. And so what is this normal vector? Well, the normal vector here, this has to be a unit normal vector. A unit normal vector, a unit normal, which is sometimes here called, is just a vector that is normal to the surface that is going directly, that is a unit vector, right? If that's orthogonal. In this case, it'd be pretty quick to see that this could be 0, 0, negative 1, because that's going straight down, and it has a vector of 1, right? It has a thing. So you could have just used n is equal to 0, 0, negative 1 here, because I think DJ does in his example. And then from there, you could actually get that since my surface is specifically on the xy plane, I could just integrate around that and transfer the polar coordinates from there. That's kind of how DJ goes about doing it, which is a very, very valid way of going about it. If you are scared of that technique and you don't want to do that, it's totally okay. This way is clearly much longer, but it does get the job done in the end. If you, for instance, and this is something that people might ask, what happens if you use this guy? Right, what if you use this? You'll get the same exact answer. You're going to get something else down here. You're going to actually get 0, 0, 1 instead of 0, 0, negative 1, instead of 0, 0, r. And the thing is, you're probably going to want to then, once you get down to here, convert this integral into a polar coordinate integral. And that's when you would use r dr d theta. Oh, sorry. That's why you use r dr d theta to kind of change it to this. We started off this parameterization using this entire thing with r and theta. So down here, we did not have to add an r. We didn't. We did not have to do that because I started off with r and theta, and it's already baked into there. If we started off with x and y and we did this parameterization, instead and we went through this whole thing, we noticed down here it would probably be beneficial for us to integrate this region with r and theta instead. Then, because we were in Cartesian, we go over the polar coordinates because, and I have to add the r dr d theta here, kind of going from that. And again, the f of r theta, right? This part comes from this part right here, right? I know that f is equal to x squared plus y squared. All I'm doing is I'm plugging in my x, which is my parameterization, right? X is r cosine of theta, y is r sine of theta, x squared plus y squared is just r cosine squared plus r sine squared. And that's how I would just get r squared here. And we're just plugging into there, right? And yeah, that's kind of where that comes from here. Polar coordinates, and so cylindrical coordinates are just three-dimensional polar coordinates, like that. Okay, so this process takes a little bit of time to kind of do. I understand, but it's kind of zooming out a little bit. I'm actually not going to do that. Really don't have much room. That's kind of the general idea for this kind of question. Does anybody have any problems with this or any questions you want to ask about this process? I hope this makes more sense here. I know 2 or 3 people asked that question, actually. I think 3 people did. Do you have any other questions? Does anybody else have any other questions on this problem?
Yeah, Nick, I have a question.
Mm-hmm.
In the purple, we did the cross product. What is the notation right here?
You mean this guy right here?
No, right below it, to the right.
Oh, this one?
We did the cross product of.
Yeah, like
right
that.
here. Yeah, right. What is that notation? What is what does that say?
R sub r cross r sub theta.
All right, thanks.
It's just a cross product of these 2 vectors that I've calculated up here, right? It is r sub r cross r sub theta. So what I'm doing there is I'm taking this parameterization and I'm taking the derivatives of every single one of these components with respect to r, every single one of these components with respect to theta, and I'm taking the cross product, which gives me the normal vector to my surface. Yeah, that's what I'm doing.
All right, I got it. Thanks.
Yeah, no problem. Okay. Any other questions here? All right. Yeah, so we have a question about mins and maxes here. Otherwise, we will kind of go from there. Let me kind of get that up. So somebody had mentioned a problem about one WebAssign here for 14.7. So let me just pull that up really quickly. 14.7 minutes and maxes. Yeah, okay. So, yeah, let me kind of pull over here. We have a lot of people asking questions. This is great. Hopefully we'll try to get to all of them. We have about like 2.5 more hours or so. So I will continue going through the and kind of going through the whole thing. So I apologize if I am not getting to your question right now. There's a lot of high volume. Let's just say that, which is great. We will not be we'll be here for the full 3 hours, which is great. So my goal is to find the shortest distance d from the point 3, 0, -8 to the plane x plus y plus z is equal to 8. Shortest distance. Okay. So if I want to find the shortest distance here between this point to the plane, this is actually a web assigned question. Sorry, this is a web assigned question. For some people, it's question 6. Is this the one you were asking for, the person? I forget who asked that question. Let's make sure I'm there.
No.
Okay.
There was one where it had like something with like an e of x times, like it was to find like
Was it e to the x times cosine of y?
yeah, something like that, yeah.
Okay, I'm sorry, because the thing is, I think if you're in DJ's class, he has different homework than
Okay,
sorry,
okay.
I think it's different. I do not have DJ's thing, so I apologize for that. So let me go ahead and write that down. And I'm assuming that you have something like the form. You have f of x y is equal to 8 e to the x times cosine of y, something like
Yes.
this. And I want to find the maxes, minutes, and saddle points,
Yeah.
stuff like that. Okay. Sorry. So this is a web assigned question. So web assigned 14.7, number 6 for DJ, and number 4 for Mo. Let's go with that. For those of you who are trying to keep score at home. Okay, so I guess the first thing I want to do, just in general, is think about how we find critical points, and how do we kind of classify them. Here, that's something I just want to at least just generally talk about, just so we kind of all on the same page. If I give you a function f of x, y, well, if I just give you f of x, right, how would I go about trying to find critical points here? If I just try to find critical points, what is a critical point, right? A critical point, if I can write the word critical, point is something where f prime of x is equal to 0, right? It has a horizontal tangent line. And I find all the points here, and then what I do to classify it, right, is I take the second derivative test. If it's greater than 0, if it's less than 0, or if it's equal to 0. If it's greater than 0, we have a concave up function. So this is a min. If it's kind of use a smiley face because it's positive. If it's negative, we have a max here, right? Because it's kind of a negative. In this case, we have no solution. Oh, well, inconclusive, really. We can't really say anything. We can't really say anything down here. We can kind of call this an inflection point in some way. But other than that, we really can't point out anything else. So in a similar way, we can do the same exact thing, with 2 dimensions. So if I now have a 2-dimensional case, which is something like f of x, y, which I have up here, to be a critical point basically means that in the x and y directions, I need to be having a tangent line that is that is parallel to the xy plane. So think about a bowl, right? A bowl at the bottom, if I placed like a kind of a line at the bottom going in the x direction or the y direction, they're both horizontal. They're both parallel to the floor in this way. So to find a critical point, we would actually need to calculate when the derivative with respect to x is 0 and when the derivative of y is equal to 0. So now, if both of these are 0, then we know that there's a critical point at a specific point. So we need both x and y to be that. Now, how do we classify these, right? How do we classify them? Well, in this case, we took the second derivative test, and the second derivative test was really quick because I only have one derivative. I only have one variable, so second derivatives just make sense. In this case, we have 4 second derivatives, right? We have 4 second derivatives. We have fxx, and we have fxy, we have fyx, we have fyy here. And what's important to realize here is that there's going to be some combination of them that gives me some information about if something's a max or a min or something like that. And it's actually taking the determinant of this matrix that I've just kind of drawn here. You can write this more formally if you wanted to as fxx times fyy minus, well, noting that fxy and fyx are the same via Clairaut's theorem, you kind of write this as fxy squared. Kind of using that. Usually, I would highly suggest you not memorize this whatsoever. Just know the determinant and calculate it from there. So this is only helpful. This is actually really helpful just to see what each one of these means. So the determinant, this determinant of this matrix can either be greater than 0, less than 0, or equal to 0. So let's think about what each one of these kind of means here. So I'm going to zoom in. I can do that. Great. So let's think about if d is greater than 0. Okay, I hope you'd agree. And this means that this constant, this term right here, must be positive. Because if it's not positive, it's automatically going to be negative because this is going to be this minus something that's positive, right? So for this to happen, this has to be positive automatically. So if this is positive, that means that these two terms must share the same sign. So either fxx and fyy are both positive, or fxx and fyy are both negative. There's two options. And so we have two options here. We have if fxx is greater than 0, or fyy is, fxx is less than 0. You can check either one. You can check fxx or fyy. It doesn't matter because they're going to be of the same sign. If fxx is positive and fyy is positive, that kind of means that I kind of have a concave up function at this point in the x direction and a concave up function in the y direction. So that means I have two concave up kind of things. And so you kind of think about that this would imply that I have kind of a bowl in this way. And so I would think about that this would be a local a minimum because I have. So this would be a minimum. Okay. If they're both a negative, that means that they're both concave down. And so you kind of think about that. I would maybe have like a sphere or a downward paraboloid or something like that. And so this is going to be a max. Okay. So the only times you can have a min or a max are when this determinant is positive and these fxx and fyy, fxx is either positive or negative. That's kind of how you get that. If it's negative, like this, what we kind of do is we realize that if this is negative here, in this case, what we can do is here we would get that if this is negative, well, one of the ways it could be negative is if this entire term here is negative. Right? If this term is negative, we automatically guarantee that this entire thing is negative. So what that means? This would mean that I would have fxx maybe going in the positive direction, and I would need them to have different signs. So fyy would be negative. So something like this, where I have some positive looking thing like this and some negative thing like that. So it kind of looks like a saddle or a Pringle, something like that. And so this is actually called a saddle point. No other information is really necessary there. If it's negative, it's automatically a saddle point. And lastly here, if it's 0, we have no information. I can't really tell you anything about it. And it's kind of the same exact thing as this kind of thing. If I give you a 0, I really can't say anything. I have to do more investigative work. Maybe try to compute this numerically, try to maybe see what's funky about it. And so with that in mind, let's tackle this question here. So if I have this question, I think we're going to do in this question here, kind of seeing this. Well, again, I want to find all the critical points and kind of classify them. So let's kind of take this. The first thing I need to do, I hope you'd agree, is take the derivative and set them equal to 0. So fx here, if I take this, is going to be 8e to the x times cosine of y. That doesn't change because the derivative with respect to x is just e to the x. The derivative with respect to y is going to be negative 8e to the x times sine of y. And I need both of these things. Oh my gosh, why do I keep doing this? I'm so sorry about that. There we go. I have now backed out of this page twice. Sorry, we're back. But anyway, so these both have to be 0. Now, if these are both 0 here, I have to check, right? The thing is, here, that I need both of these to be 0 to make this happen. So let's take this first one here, fx here, to be 0. And always, before you start to classify these things, you need to make sure it's a critical point. It's very important to do that. You can't just plug in any random point here. You have to make sure it's a critical point and then go to this step. Always, it will always be that. So in this case, well, if this is equal to 0, this means that either this function is 0 or this function is 0. Either e to the x is 0 or if cosine of y is 0. Now, in this case here, right, if e to the x cannot be 0, so this can't happen, right? E to the x can't be 0. It's impossible for it to be. The only chance I have is if cosine of y is 0. Okay. When is cosine of y 0? Well, cosine of y is 0 in a couple different places, right? If I kind of look at this kind of trajectory here, cosine of y is 0 up here and also down here, right? So it's at pi over 2 and 3 pi over 2. And so basically what I'm doing is every single time I move, let's say I start up here, right? Every single time I move another pi, I'm going to get this to be hitting 0. So kind of imagine that y could be something like, plus or minus pi over 2, plus or minus 3 pi over 2, and so on like that. It's infinitely many times this could happen. And so you can maybe write this maybe a little bit more succinctly as just saying, oh, I'm pi over 2 plus n times any number pi times pi. So n is any number, any positive or negative integer. This will always hold. So for all of these values, this top one will be 0.
Nick, do you have plus or minus n pi?
No, so I don't actually have to say that, right? N can be anything from negative to, like, n can be, I'll write this, 0, plus or minus 1, and so on, like that.
Okay.
Yeah, that's what I'm kind of writing that. So we then see here is, okay, well, if that happens, let's plug in y into this. So we get negative 8 e to the x sine of, let's go with pi over 2 times n times pi equals 0. Right? I now plug in, I found what y has to be, and I kind of come back to here. So in this case, again, this e to the x can't be 0. So the only chance I have is if sine of pi over 2 times n pi is 0. And can that ever happen? Well, plug in sine, for instance, pi over 2. Sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1. And really, any multiple of this, anywhere where cosine is 0, sine is 1 or negative 1, right? And so this can't happen. So therefore, because of this, this can't happen, and thus there are no critical points in this surface here. Because of that, because these two things are not satisfied always. There will never be a y, there will never be an x such that these are satisfied. The 8 is irrelevant. Right? I could put any constant in front of here other than 0. This will always be that too. And as somebody else in the comment commented, well, if this happens here, I can't have fxx be 0 as it is. Right? If fxx is 0 here, I'm automatically going to be negative or 0. Right? Because that kind of goes away. So I kind of have to assume that fxx and fyy are non-zero here. Right? If fxx is 0, this entire thing goes away, and it's automatically going to be either negative, or if this is also 0, that will be 0 too. So yeah, that's kind of what we do there. Does that make sense? Does anybody have any questions about that? Any questions here? Okay. So the next thing I'm going to do is kind of on this list of fun questions. Let me kind of see what question this is that somebody asked here. One second. Yeah, so we can talk about spring 2018 question 8C. We're going to do that. I'm going to move over there now. You know, Brandon asked a question about if you'll be given the points to see if they're critical points or not. they have to give you a really easy one, or they'll have to kind of, because finding the critical points can be kind of taxing. But if they only give you one that has one, then maybe it's not too bad in that case. Most of the time, it seems like these questions are going to be like, is this a critical point? Is this not a critical point? Is this a saddle point? Kind of working from there and kind of just manipulating that. Otherwise, yeah, it really depends though. There could be definitely a question where it asks, find the critical points and classify them. That's a very reasonable thing, but they can't do a very long one because as people are well aware, these can take really, really long time, unfortunately. So this is spring 2018. 2018. Number 8C specifically here. Okay, so in order to do this problem says the following. I'm going to consider the point A, 2, 0, 1, and consider the B, 0, negative 1, 2. And I would like to calculate this integral, ds, where C is the line segment from A to B. Okay, that's what this problem is. All right. So I am aiming to do this. Now, the first thing we need to realize is what is this integral kind of saying? What do we have to kind of do to kind of evaluate? So ds here is related to arc length. I am on my curve. My curve here, my line segment is from A to B. So this is some flavor of f of xy as z ds, right? Something like this. And the only way I really know how to kind of go about this problem is to kind of just go brute force here, because I don't have any other techniques. This is not a vector field. This is just this. So this is kind of computing. In this case, because it's 3 variables, could be thinking about something like a mass of this sheet that you're creating to, or the mass of this wire, this very thin wire. Unnecessary to think about the application here, especially in this context, but it's highly dependent on the context. So to do this, right, what we do is we kind of parameterize, and I plug in my parameterization. And because this is a scalar function, to replace this ds here, I need to do it with the magnitude of r prime of t dt. So in order to parameterize this curve, I am doing this line segment from A to B, right? And the formula for parameterizing a line segment, r of t, is 1 minus t times r0 plus t times r1. If you didn't want to use this technique here, you could also use that r of t is equal to r0 plus t times v and find your direction vector. I'll show both ways just to kind of show this. Using this first way here, r0 is A and r1 is B. So this is going to be 1 minus t times, what is my point here? Sorry, 201, my area code. I'm not going to give you the other 7 digits, plus t times 0, negative 1, 2. And this. And so we combine these. This will be 2 minus 2t, 0, 1 minus t, plus 0, negative t, 2t. And adding them together, we would get, this is going to just be 2 minus 2t. This one's going to just be negative t. And this one is going to just be 1 minus, 1 plus. Now, if we use this formula, we always know that this time is always going to be between 0 and 1. We always want our domain here, our line segment. Because again, if time equal to 0, this goes away. No, sorry, if time equals 0, this stays and this goes away. So I'm at R0. At time equal to 1, this entire thing goes away and I'm left here. So I'm at R1. If I want to use this technique instead, as a reminder, how do I calculate my direction vector? My direction vector here could be calculated as R1 minus R0, right? The points kind of subtracted from each other, which would be 0, negative 1, 2, minus 201. In this case, this would be negative 2, negative 1, and 1. I did it that way. And therefore, R of t would be this. R of t would be equal to r0, which is 2, 0, 1, plus t times this vector, -2, -1, 1. Or more formally, 2 minus 2t, negative t, 1 plus t. Same thing. Same exact thing. Here we go. Now, this time you would have to remember that if I did do this r1 minus r0 bit, this time is also from 0 to 1, how you've computed this exact thing. The way you can check that is at r0, I'm at 2, 0, 1, just plugging it in. At time equal to 1, I'm at 0, -1, 2. And you can just plug that in. But the way you construct your direction vector here, r1 minus r0, is exactly the same exact way that we get this formula, this nice kind of parameterized formula here. So with this in mind, I have this parameterization, however you want to go about it. What I have to do, if you kind of notice, is I'm going to have to compute the magnitude of this vector, of the derivative. The derivative here is really, really simple, though. So r prime of t is just equal to basically, the coefficients in front of the t's here, which is -2, -1, 1. And the magnitude of r prime of t, which I need, is just going to be equal to the square root of 4 plus 1 plus 1, which is equal to the square root of 6. That's all kind of nice. And so I want to calculate f of r of t here. So I'm going to plug in wherever I see x, I'm going to plug in my x component. Wherever I see y, I'm going to plug in my y component. Wherever I see z, I'm going to plug in my z component. So f of r of t here is just actually equal to the sum of these three things. 2 minus 2t plus -t plus 1 plus t. And kind of doing this out, I would get, I think I get 3 minus 2t. So kind of see that. Yeah, I think I get that. And so lastly, to finish this off, I now calculate this integral. Calculating this integral would be between 0 and 1. I'm sorry, I calculate this integral up there. This integral now would become, in this case, we would get 3 minus 2t times the square root of 6, right? dt. So we just evaluate from there. The square root of 6, we can then do 3t minus t squared from 0 to 1, and get this probably to be square root of 2 square root of 6. I think that would probably be the answer here, which is my answer. So as a reminder, a couple of really good points to remember here. The equation for a line, which is r0 plus t times v. Don't forget how to create equation for a line if I have 2 points, if I want to come up with the points going through it. But I think you actually do in part A of that question. So you can actually just use the same exact thing that you just did in part A, but this is just kind of going through the whole thing again. And then kind of reminding ourselves that we have 1 minus t times r0. Oh, kind of remember that how to evaluate this integral, right? We parameterize our curve. We then multiply it by the magnitude of r prime of t. Substitute in all of my components for r of t here, for f, kind of x, y, and z. And then go from it and just kind of integrate. At this point, it's not too bad. Do you have any questions about that?
For the first time finding like r of t, could you just go through how you found the domain of t again?
Sure. For which one? The first or second one?
First one.
First one here?
Yeah.
So if you note here, at time equal to 0, r of 0 here is just equal to 1 minus 0 times r0 plus 0 times r1. Right? This is r0. That's all nice. And then at time equal to 1, I do the same exact thing. And I get 1 minus 1 times r0 plus 1 times r1. And again, that goes away, so I'm left with r1. So I started r0, I ended r1, and so therefore my domain is from 0 to 1. Like that. And part A is honestly the exact thing that we just did here. Part A is literally this, of this question. The only thing that changes is that this domain here, where I'm trying to find the parametric equations. So the parametric equations are just when x, we write this out more formally, like parametric equations are when I have like my x is equal to 2 minus 2t, my y is equal to negative t, and z is equal to 1 plus t. And if I'm just trying to find, for instance, the parametric equations from the line through a to b, my domain is everything. Right? There's no restriction. This is only for a line segment that I have this restriction here. So my domain would be everything. So I have to come up with that. Yeah, that's part A. Any questions here? Okay. So I'm trying to go through everything here where the people are saying here. So we have a Stokes question that we want to do here. Let me see. The person that asked this, is this the are you in Mo's, Victoria, are you in Mo's or DJ's class?
Mo's.
Okay, so you have the, is it over the hemisphere here? Kind of that one?
Yeah. Yeah.
Yeah, okay, good. Just want to make sure. Because I don't want to be doing a random problem here. I'm going to go down this way. Okay, do that. Okay. So now I'm going to talk about Stokes Theorem here. So Stokes Theorem, we're asked to evaluate this integral right here, the double integral over my, we're trying to just calculate this curl f dot ds, where f is equal to this very, very fun thing, z e to the y, x cosine of y, x z sine of y, where s is the hemisphere, x squared plus y squared plus z squared is equal to 25, where y is greater than or equal to 0, oriented in the positive the positive y-axis. Okay. So a lot happening there. So let's first off kind of remember what Stokes Theorem is saying here, just overall. I have 25. Do you mind if I just use 25, my number here? I can just use that. It's not going to be too much of a difference. That kind of works through there. So when I'm trying to work with this, the first thing to realize here is, what does Stokes Theorem say? Stokes Theorem is the three-dimensional version of the Green's Theorem. It's actually, Stokes Theorem is a very general version of Green's Theorem. Green's Theorem is actually a simplification. It's just a two-dimensional version of Green's Theorem. So what that says is, if I want to find the amount of work it takes to move an object around a vector field, and I have this curve C, which is a closed curve, what I could do is I can actually calculate this and change this to a surface integral, where S here, C is the boundary of my surface S, the boundary of my surface S. And this becomes then the curl of f dot ds. Now note, this integral right here is the same as f dot ds, but my vector field f is just the curl of f. It's just that vector field. So I hope you'd agree a couple things. First off, so a couple things that have to happen. These orientations must be the same. How do I put this? Same orientation. Now, what do I mean by that? What I mean by that is as follows. Every surface is oriented. What I mean by that? What that means is I have a normal vector that is going in a direction. So for instance, in this case, we have this problem, which is x squared plus y squared plus z squared equals 25, where y is greater than or equal to 0. So something like this, where y is greater than 0, so y is over here, x is here, and z is here. I'm going to try to make a sphere as good as possible. It is not ending well. So this is at least my attempt at a sphere. Forgive me, math gods. Here, so this is at 5, and I'm told that my normal vector is pointing in this direction here. Okay, it's pointing in the positive y direction. That's what it tells me, positive y-axis. Okay, so my normal vector is pointing in this direction. So what does that really mean? So in total here, what I need is my normal vector and my curve to be matching up to the right-hand rule. Okay, I need it to be matching up to the right-hand rule here. So what does that mean? If my normal vector is going one way, I need to be wrapping around. I'm going to draw this actually in a different way here. Just kind of visualize this. If this is my surface here, F, I have two normal vectors. I have one this way, or I have one this way. To use Stokes theorem, if I want to use Stokes theorem with the black arrow here, the one that's pointing upwards, this normal vector, I need to think about the right-hand rule. So if I'm pointing upwards, I need to be curving in that direction, right? I need to be curving in this direction like this here. So the orientation of this curve, C, must be in this direction. If my normal vector is pointing downward, my normal vector must be pointing in the exact opposite way. Like I need to be thinking about my curving in that way, the curl there. So in this case, we have to come up with a couple things. I hope you'd agree that computing the curl of this would be, how shall we say, horrifying? And also, because think about what I'd have to do. I would have to parameterize this surface. The only really good way to do this would be via spherical coordinates. I mean, I want zero things to do with that, especially in a parameterization where I'll have to calculate r theta times r phi across r phi, right? I'll have to calculate that. That's something I do not want to do at all if possible. So maybe what I could do is I could use, instead of the first way, I can go the second way of Stokes theorem, kind of going the exact opposite way. Once I compute this, I would like to find a curve that has the boundary of this surface. So I hope you'd agree the boundary of this surface, well, if it's just the Tupperware, again, I'm coming back to the Tupperware thing. If we're just the Tupperware here, I hope you'd agree that this curve right here could be the boundary of this. Because again, I'm just considering the top here. So just thinking about the top, I'm considering just this bottom part of the Tupperware. So my curve here is this guy. Okay, that's my curve C. Now, which direction is it oriented? This is a really important thing to think about. The orientation here, I need my normal vector to be pointing this way. So if my normal vector is pointing this way, I have to be curving in this direction here. I have to kind of be pointing this direction here. So in order to do that, my orientation must be in this direction. Okay? So it kind of has to be to make this work. So what does this look like just in general? What does this curve look like? Well, it's on the, I hope you'd agree, it's on the XZ plane. It's a circle of radius 5. And which direction is this? Well, I am going from the positive Z axis to the positive Y axis. So that means I'm actually going in this direction here. Kind of going around in this way. This is my orientation that I'm worried about. And this is my curve C. So this is a little bit easier, I hope you'd agree, because this curve is not too difficult to kind of go for. So if I want to kind of work with this, and I want to kind of parameterize this curve now, to kind of work with this, right? There's a couple different things I can think about. The first thing is let me just write this a little bit more formally here. The curl of f dot ds is equal to, so this right here, the curl of f dot ds, this is now equal to the amount of work it takes to move an object around this curve in this direction. I hope you'd agree that this curve right here is in a counterclockwise, in a clockwise direction, which is kind of hard for me to deal with, to parameterize. So if I want to go the exact opposite way, going this way, boop, what I do is I flip this, and it becomes a negative C, but I have to put a negative out in front. I flip the orientation, I have to go the exact opposite way. And again, now what I could do here to evaluate this is I need to parameterize this curve, because it's really a three-dimensional curve, unfortunately. It's a three-dimensional curve. And I need to parameterize this somehow. So let me kind of go ahead and try to do this. The first thing to realize, if I want to come up with R of t, I would hope you'd agree that the y component is 0, right? I'm always on the xz plane, so the y component is 0. Then the x and z kind of act like polar coordinate things, right? Where this is 5 cosine of theta and 5 sine of theta. So I kind of consider this as 5 cosine of t, and this is 5 sine of t. And I'm going between 0 and 2 pi. So I'm going around the full circle. Okay. So now, if I want to evaluate this, what I need to do first is, as a reminder, this needs to become here. I'm going to put a negative out in front, my negative curve C, or in this case from A to B. I need to evaluate the vector field at my parameterization, take the dot product with the derivative, dt. Okay. So in order to do that, I take my derivative here. My derivative here would just be actually very nice. It's negative 5 sine of t, 0, and 5 cosine of t. That. I now want to evaluate this vector field with this here, right? F of r of t. If I see this, well, this is actually really ugly, but everywhere where I see a y, there's going to be a 0. Well, that's beautiful. So in that case, this entire part here is just going to be the x coordinate. This entire thing is going to be 0. This z component is just 0 because sine of y is 0. So in this part, this first part is just the z, which is just 5 sine of t, e to the 0, which is just 1. This becomes 5 sine of t. This second part here is x times cosine of y. Cosine of y is 0. This becomes x, which is just 5 cosine of t. And this last part is 0, which is all beautiful. So now we take the dot product. I'm going to do this outside of the integral. It's going to look a little bit easier. The dot product of these two things here is actually relatively quick, if I'm not mistaken, because this is going to be 0 and this is going to be 0. So I'm just left with negative 25 sine squared. Sine squared of t. And so therefore, this then becomes, the negatives cancel with each other. This negative and this negative cancel with each other. And so I'm left with 25, 0 to 2 pi of sine squared of t dt. And now I just integrate this guy. That's where this kind of comes out to be, I think, at this point. So we can kind of integrate this sine squared. I can evaluate this utilizing a double angle identity. Right, this could be 1/2 times 1 minus cosine of 2t, dt. This first one here, this is going to be 25 times 1/2 times 2 pi, right? This first one is that. Here, minus, well, the integral of cosine of 2t is a sine of 2t over 1/2. This becomes 1/2 sine, 1/4 sine of 2t. Evaluate between 0 and 2 pi. And I hope you'd agree this entire thing would just be 0 because sine of 4 pi is 0 and sine of pi is 0. This is also a periodic function on a periodic domain. So therefore, this entire thing would be 0. So just kind of looking at this, this is just equal to 25 pi. And that is my answer. So working our way back with a terrible pun in there, what we do is realize that to kind of use Stokes Theorem backwards, we need to find the boundary curve first. We need to make sure we have the correct orientation. And we follow the right-hand rule. That's kind of the basic goal there. Then what we see here is we can then evaluate this integral here as we usually do, right? We can't use any tricks that we know possibly other than the fundamental theorem of line integrals. We can't use Green's theorem because it's the three-dimensional thing. We're already using it. We can't like double do it, unfortunately. It can't work that way. And F is not conservative anyway, so we can't do that. We can't use the fundamental theorem of line integrals. So what we do is we parameterize a curve. We calculate this using this formula as we have f of r of t dot r prime of t, and then we just evaluate it at that. We get our answer is 25 pi. Does anybody have any questions about that? Does that make sense, Victoria here?
I'm still a little bit confused in terms of the orientation. So our normal vector is going towards the positive y-axis, but I'm still kind of confused on how you know which way the boundary curve itself is going.
So you follow the right-hand rule. So put your thumb in the direction of the normal vector, and then curl your hands. That curling of your hands has to be the direction of the curve. So if I kind of look like this, right, my vector must be pointing in your way, it's kind of pointing in this direction. I have to kind of go like this. Right? And my vector has to be curling towards the positive x-axis here to kind of make that kind of happen.
Okay.
Yeah, so it has to follow the right-hand rule. That's the big thing. Anyone have any other questions here on this part?
How did you know that the normal vector was pointing that way?
It says it in the question.
Okay, cool.
Yeah, it says oriented in the direction of the positive y-axis.
Okay.
So, yep, if it does not say it, which would be kind of sad, you honestly just assume a certain way and work from there. Yeah, in these problems though, you're 99 times out of 100, it will tell you which direction to go in. Yeah. Any other questions here? Okay. With that in mind, I am going to go to spring of 2017. I think here, let me just check really quick. I'm going to go spring 2017, question 11, which, yeah, I'm going to do that question. And I was asked, again, talking about the divergence theorem here, it's good to always practice that more. I'm going to move over this way. As soon as this, by the way, as soon as this video starts rendering, it's a 3-hour video, so it might take a little while to render. I'll post this on YouTube as quickly as I can if you guys want to review anything. But also, I'll post right after this, just so you can also do this. I'll post right after this the whiteboard, so you guys got to go back and kind of see what we did. My whiteboard currently is not in the best direction. I don't know why I always go down like this, but that's my life. Like that. That's okay. So I'm going to do question 11 from spring 2017. Question 11, spring 2017, which talks about, again, a flux integral. All good stuff to do. So F is my vector field here, which is the vector field x, y squared, and 2z. I want to find the flux across my surface S, where S is the boundary of the solid region, E bounded by the paraboloid z equals x squared plus y squared, and the plane z equals to 2. Okay. So with this in mind, let's first off draw this out. Now the first thing, I want to compute the flux. So again, I'm trying to compute this integral right here. Yeah, right? Trying to compute this flux integral. Now, whenever I'm doing this type of problem, right, there's only 2 ways I know how to compute this. There's literally 2 ways. I have 2 ways. The first way is the brute force method, right? The first is I parameterize my surface, and I compute this where as we kind of at least mentioned last part, data with RU cross RV, dV, sorry, dA. Right, this is one way I could do it. But if I notice something about my surface, if F is bounds a volume E, if it completely bounds a volume E, then I can calculate this using the divergence theorem. Like that. Okay, so there's really 2 methods I only can use to evaluate this. I either can just go brute force this, like that, or I can calculate the divergence of F and kind of integrate over my volume term. In this problem, we are given that we have the surface is the boundary of the solid region. So it's 2 parts to my boundary. We have the paraboloid, like this guy. Oops, I've missed my turn here. Kind of like this. And I'm also told that I'm also thinking about the plane z equal to 2. So my entire surface is this thing right here. I'm my entire surface F. And what's really nice here in this case is I can see actually visually that I am including both the Tupperware and the lid itself on top of that. And so because I'm including both of them, I have a fully bounded surface, which bounds completely a volume. And so because of that, I can then use the divergence theorem here. Instead, because I can then calculate just my volume E. So I can utilize this thing because I've completely bounded my surface. So in order to do that, we first off compute the divergence of F. The divergence of F here is the derivative of each one of these components with respect to the variable. Like, so this is with respect to X, this is with respect to Y, this is with respect to Z. It just so happens that each one of them is just of those variables in this case. That's just very, very rare. You have that. But this would be 1 plus 2y plus 2, or you get 3 plus 2 times y. Actually, this is the divergence here of this vector. So what this entire problem comes down to solving is just a triple integral e of 3 plus 2y dv, where e is this entire boundary right here, where e is this entire volume. And so all I'm trying to do now is come up with my bounds of integration for this. That's really it. So with this in mind, this is actually kind of a weird thing. I'm just going to pause here really quick and kind of say something. If you're coming from a teacher's perspective, and you see you have so many different parts of your, like you have so many different parts of, like so many different problems that you can do in this class. We can ask so many different questions, right? And there's only 2 hours. There's such a limited amount of time I can ask you for 5 chapters of stuff. Something like this is really, really nice because I'll tell you why. This includes a lot of really good information for me. First off, it tells me, do you know how to use the divergence theorem? Second off, do you know what flux means, right? And thirdly, I don't think I stressed this enough. I don't think this is stressed enough here. You now have to compute the bounds of a triple integral. So they might not ask explicitly a question about a triple integral. They might inherently, in a divergence theorem question, ask a triple integral question. And so this allows people, I mean, as a person that made an exam this winter, it allows me to kind of incorporate a lot of interesting and important material that we might not have time to cover in the exam into one question. Just something to think about. Like this is actually a really good question because it tests a lot of stuff. From a teacher's perspective, it's a very good question because of that, because it includes a lot. Okay, tangent over. But be that as it may. We're now going to come up with the bounds of integration for this. So I hope you agree, the bounds of integration for this are actually, the first thing I see here, right, when I'm thinking about my bounds of integration, I see that probably the z coordinate is probably the best way to think about this first, right? I see that if I enter from the z axis, if I enter from the bottom and go off of the top, I'm always entering from the paraboloid. I'm always exiting from that top plane. So you gotta think that z here is bounded below by x squared plus y squared, and is bounded above by 2. Right? Those are the 2 points. I have my paraboloid and bounded by the top. Now what I do once I've integrated out z, I project onto the xy plane here. Onto the xy plane here, well, I'm going to get a circle. Now, what's the radius of that circle? Well, that circle here is this circle, I hope you'd agree, this top circle right there. It's this circle, which is the intersection of the paraboloid and the plane z equal to 2. And so that's really x squared plus y squared. Remember, z is equal to x squared plus y squared, and z is equal to 2. So it's the intersection of these. So you get x squared plus y squared equals 2. And that's this circle. So this is actually the radius of the square root of 2. Here. Now, I see this here. I see that this can be integrated really well using polar coordinates. So because of that, I'm going to go back up here and change this. I'm sorry, this is actually squared. I'm going to go change this now to cylindrical coordinates because I want to integrate this via cylindrical coordinates here. So what I'm going to do is this gets exchanged for r squared. And then I'm going to do r at theta. Theta is really quick, 0 to 2 pi. That's my full circle. And r here is from 0 to square root of 2. And these guys are my bounds. And so now I go ahead and try to compute this integral. So this is r squared to 2, 0 to the square root of 2, and 0 to 2 pi. I replace my y here with r sine of theta. And I have to multiply by r here because that is my change of variable. And now integrating this guy is what I want to do. That's how we kind of get this problem. Does anybody have any questions? I don't. Just do you want to see me go through integrating this? Does anybody want me to see me go through integrating this, or can I just leave it kind of there? I think that's okay. You know, the reason why I changed the cylindrical here was because I saw that, you know, my bounds were from x squared plus y squared to 2, and when I project onto the xy plane, this region could be described very, very well with polar coordinates, right? So if I want to integrate this completely in terms of polar coordinates and cylindrical coordinates, and so I want to basically kind of expand that and go to cylindrical coordinates. So yes, so cylindrical coordinates are the three-dimensional version of polar coordinates, just in general. Right? All I'm doing there is I'm just extending this. I'm on a cylinder, right? So this is always a circle, and I'm just including z here. I'm just including a height, right? If I had no height on my circle, right, it would just be that. So here I noticed that this paraboloid can be written very, very simply using polar coordinates, or using cylindrical coordinates, which is equals r squared, and therefore my bounds can be written really, really nicely. The more nicely I can write my bounds, the better, honestly. So that's why I changed to cylindrical coordinates here. You could do this all via Cartesian coordinates. It would become very, very difficult once you've integrated one thing out. At least I think so. It would become a little bit difficult. Anybody have any questions about this problem other than that?
So why did we include the extra r term at the end, you know, the r dz dr d theta? Is that because we changed to polar after setting up the integral?
So we changed the cylindrical afterwards, yes. In these problems for triple integrals like this, we always need to change because we set everything up almost all the time with Cartesian. So if we have x, y's, and z's, and then I want to change it, I have to include it.
Okay.
Yeah. Otherwise, if I've set up the entire problem and this integrand is already in, you know, my R form, then I don't have to. But that's only really the only time you do that is when we have like the flux integrals. If you just have a straight integral like this, you always have to change to r dz dr d theta, or the rho squared sine of phi. Yeah. Any other questions here? Okay. I'm trying to go through some more. I have a spring 2018 question 6 on deck. Yeah. Okay. So let's do that. Yeah. Okay. So I have spring 2018 number 6. 2018. I'll move my thing really quickly in a second. Ooh. All right. So this problem says compute the area of the part of the plane z equal to 1 plus 2x plus 2y that lies above the triangle with vertices 0, 0, 1, 0, and 0, 4. Okay, so it wants me to compute the area, this area of this over this domain here. So the first thing we need to remember is how do I compute the area of something? And if I have a surface integral, if I have a surface and I have a parameterized surface here, the important thing to remember is the area of a surface is actually just the double integral of a 1 dx, right? This is the area of a surface. And what's important to remember here is if I parameterize this, what happens is this becomes the domain D of RU cross RV, the magnitude of that, dA. And so this is the surface area. So if you're asked to compute surface area, that's what you compute it. And so in this problem, we have this guy over this interesting triangle here. Let me kind of draw this out. We have 0, 0, 1, 0, and 0, 4. There was a little bit of a typo in this question. That guy. So it's over this domain here. And so if we look at this, and I want to kind of evaluate this, the thing I need to come up with first is my parameterization. Now, what is my parameterization for this curve? Well, if I have a plane, it becomes very, very simple what my parameterization is. My curve here is actually just, I give you the x, my surface here is I give you the x, I give you the y, I can give you the z. Right? So if I have anything of the form like z is equal to f of x, y, for instance, I can have a really easy parameterization of x, y, f of x, y. And in this case, my x and y, I project onto here, and this domain is actually really easily expressed in terms of x and y. So I can just do that. So because of it here, I'm going to parameterize my domain, R as x of y, R of x, y here, which is equal to x, y, 1 plus 2x plus 2y. And my domain, I'm going to call this domain D here, and my x and y are in this domain. If I need to, at the end, I can start to come up with the limits here. I'm not going to try to worry about that too much at the moment. If I need to, it's okay. Well, but it can be easily expressed here, I hope you'd agree, in Cartesian coordinates. So now what I need to do is I need to calculate RU cross RV. So in this case, I need to calculate Rx. I need to calculate my pharmacy, which is, in this case, it's just 1, 0, 2. Ry is equal to 0, 1, 2. It should kind of make sense. This should make sense that this should be a constant, right? A constant vector, because a plane always has the same normal vector, right? Always. Because it's a plane. So it should make sense that way. Rx cross Ry then. So the cross product of these two vectors, 0, 1, and 2. 0, 1, and 2 here. That. And we have a 0, 1, and 2 down here. My I component here is going to just be -2. My j component here is also going to be -2. And my k component here is going to be 1. And so what I need to do is I need to calculate the magnitude of this. The magnitude of Rx cross Ry is equal to the square root of 2 squared plus 2 squared plus 1 squared, which is the square root of 4 plus 4 plus 1, which is just equal to the square root of 9, which is 3. And so therefore, with this in mind, the area of this then becomes the area of the surface is then equal to the double integral over d of 3 dA, which is a 3 times the area of my domain D. And this is my domain D here. So it's just calculating the 3 times the area of this triangle right here. Triangles are really nice to do, 1/2 base times height. So 3 times 1/2 times 1 times 4, because it's that 4, it's that 1. And so this is 6. Not 6 factorial.
Nick, I have a question. When you
Yeah.
do this, and if you get that the magnitude isn't equal to a constant, can you not just multiply the constant by the area that you find? Like
Because
that?
of this, yes, you always can.
Oh.
Yeah, because of this specifically, yep. But we just did down here, yes. If your domain is really simple and you can calculate that just by, coming up with either geometrically you can do it. Yeah, sure. If it's tougher geometrically, then you might have to go through and come up with bounds.
So it's whatever you find geometrically multiplied by whatever the magnitude of the cross product is, no matter if it's a constant or some kind of function inside of the
If
square
it's a
root or anything?
function, you have to go through the full process.
Okay.
If it's a function, you do have to go through the full process of integrating this fully out. If it's a constant, though, you can pull
Yeah.
this out, and then it becomes a 1. But if this was like, let's say, a y, I couldn't do this. I'll have to come up with the bounds of this triangle.
Okay. Okay.
Yeah, I meant to figure that out. Okay, any questions here about that? Any questions?
If you're parameterizing it with x and y, like, do you have to put the surface area is equal to the magnitude of Rx cross Ry, or can you just write the surface area is equal to the square root of 1 plus Fx squared plus Fy squared?
So please, under any circumstances, please don't do that second one. Don't memorize that. Doing this entire thing is so much better. I honestly, I hate so much how Stewart does that, or why they just go ahead and write all these simplifications. You can do that, sure, but it is so unnecessary to kind of go through that, because this process is not too much more difficult than kind of going through and writing out 1 plus Fx squared plus Fy squared. If you write that, it's totally okay. I think that'll be fine. I don't see any reason why that would be a problem. But it is, I promise you, it will make your life so much easier if you honestly forget that from your memory and just go through this entire process again. You want as least cluttered things as possible going through that. Yeah, but that's okay. If you want to go about doing that, yeah, go ahead. That was a really, really aggressive answer to that, and I'm sorry. I'm sorry about that, but it's just important to kind of make sure that you can do that, yes, but it would be really, really more beneficial for your time to kind of make sure going through this process here, especially because if you go through this process here, you'll get more partial credit than maybe if you made a mistake somewhere.
Okay, thank you.
Yeah. Any other questions here? Okay. So we were asked then, the next one was number 9 on spring 2017. Three-dimensional potential function. Sure. Okay, so I have a vector field F, which is equal to y squared cosine of x plus z to the third, -4 plus 2y sine of x, and 3x squared z plus z. And I basically want to find a potential function such that this, such that the gradient of it is equal to this function, equal to this vector field. So as a reminder, we don't have to do this because I don't think you guys really learned this that well. You guys just didn't even learn this in class. That the curl of F, right? To see if a vector field is conservative in 3 dimensions, we check if the curl of F is equal to 0. So in this case, we'll just have to assume that this curl of F is equal to 0. Totally okay. And so we assume that there is some potential function. There's a function phi such that the gradient of it is equal to this vector field here. So we know that this means that a 3-dimensional vector, right? Phi x, phi y, phi z. And so we know then that this means that this derivative of this potential function with respect to x is equal to this x component here. X plus z to the third. We have phi sub y here, which is equal to -4 plus 2y sine of x. And lastly here, phi sub z is equal to 3x squared z plus z. Okay, so I want to basically find a function such that the derivative with respect to x of it is this, with respect to y is this, with respect to z is this. How do I go about this? Well, it's pretty similar technique as you would use in the one-dimensional case. In the one-dimensional case, what am I talking about? In the two-dimensional case.
I think it's 3xd squared, at least in the.
You know what's really bad? I did the exact same thing yesterday. Oh my god! Thank you. So it's gonna mess me up. Thank you for checking that.
You're welcome.
Great. Oh my god. Sorry, everybody. I can't read apparently today or yesterday. So your first thing here that you want to do, as always, kind of as always in these problems, is there's a technique that we did in a two-dimensional potential function that what we did is we integrated with respect to x and we integrated the other one with respect to y and we kind of matched it up. That will not work here because there's just too complicated, and honestly, just too complicated of a problem to do that, and there'd be too many matching things. And we'll show you why. So the first thing you're going to want to do, and this is the same process you can use every single time here. Every single time when you go through this, it's the same exact process. So the first thing we do is when we integrate with respect to x, I'm going to integrate this function with respect to x here. Okay? Dx. So I'm going to integrate this. This will get me back up to my original potential function. Integrating this with integrating cosine is just sine, so it'll be y squared times sine of x plus x z to the third. And now we have to be very careful because in the two-dimensional case here, right, we do have to always make sure that when I integrate, I have to include a function of just y, right? But in this case, because I have two variables here, I could have a function, say something like, you know, I don't know, y to the third times z to the fourth here. And if I took the derivative of this with respect to x, I hope you'd agree I would get back down to here. And so what I want to do instead is there could be a mixed function here of a function of both y and z, where if I took the derivative of this with respect to x, this entire thing would go away. It's kind of a constant of integration. It's a function of integration, specifically of two variables. And so because of this, we now want to find this g of yz. Now, in order to find this g here, well, we have two other functions here that we kind of play with. This first one here is if I took this function with respect to y, I could set it equal to this, I could maybe find the derivative of this function with respect to y. So let's kind of work with that. So taking this derivative with respect to y here, this first part here is 2y sine of x. And this second part here, this goes away. This third part here is the derivative of g with respect to y. So it's g sub y here, not a prime, it's g sub y. And therefore, this has to be equal to this guy. And so we can kind of match these up. You can kind of see that they share the 2y sine of x, but we see that g of y then has to be -4. Okay. Now, what I could do is I could just integrate this back up with respect to y, right? I can integrate this with respect to y now. And getting back up to my original function, this whole thing would then become -4 times y. But when I integrate with respect to y here, this is a function of both y and z. So therefore, there has to be a function attached to this that could be added. It could be just a function, just a regular z. Here. Just like that. So if I kind of move down now, in this case, I can then get that my potential function here is now equal to y squared sine of x plus x z to the third plus, minus 4y plus h of z. And now I need to find what this h of z is. And I have one other option of doing that, right? I only have this one last little piece of information that I continually write incorrectly. And I need to have this piece of information now. So the way to do that is now to take this function with respect to z, derivative. So let's do that. Piece of z here, this term goes away. This one becomes 3x to z squared. And this goes away, and this becomes h prime. And we can write h prime because it's only dependent on one variable. And now we know that both of these have to be the same. And we know here that they share the 3x z squared. And therefore, h prime of z has to equal z. And therefore, this means that h of z, integrating this, is z squared over 2. There could be a plus k here if you wanted to at the end here. It's not necessary at all, though. Because we're finding a potential function, not a general potential function. And so lastly here, this means that my final answer is equal to y squared sine of x plus x to z to the third minus 4y plus z squared over 2. And this is my potential function. So the process here is the same exact process you can utilize. Honestly, you can utilize this in the same exact capacity as you do in the two-dimensional one. It's just a little bit more work here. What we have to do is we kind of play around and we kind of keep trying to find our function. We kind of have to find really two different functions here. We have to find the g of y z, then we have to find this h of z term. And you can do this in this order. You can do it in any order you would like. Honestly, I just like it's almost always this. There's no real technique here to figure out which one's going to be the easiest to kind of do in order. So I just will go with x and y and z. So it's going to work out this way. Does anybody have any questions about how I've done that? Or any other points here? That sounds good. Okay. I now have here a question about, if we want to keep going, let me see. I don't know what. I'm sorry, give me a second. Am I here reading this weird? Fall 2018. So, okay. So I have here spring 2018 number 5. Oh, again, more potential functions, which is cool. We'll just do the two-dimensional version of this and go from there. Probably a good extension of this. Okay. So in this one, this is spring 2018, problem 5. And this problem entails that I have a vector field F here, which is equal to e to the y, x e to the y plus 2y here. And I would like to do all parts here. I think that's kind of what we do. The first part here is F conservative. And in order to do that, right, while we're kind of thinking about this, I usually name this P, usually name this Q. To find out if F is conservative, usually let Qx be equal to Py. Is this true? Right, that's what we kind of have to find out. And here what we do is we note that P sub y is going to be equal to e to the y. Q sub x, this goes away, and so we're also left with e to the y. And so because of this, we get that Py is equal to Qx. Great. So that means that F is conservative, which means that there is a potential function such that the gradient of it is equal to my vector. Part B here, going from that, is the integral CF dot dr. Let's calculate this, where C is a counterclockwise circle. So 4 C's in a row, sorry. It's a lot. Of radius 3, centered at 2, 3 here. Now, an important point here that I want to make, and this is, I will draw this nice little chart again that I had in the past. Whenever you're trying to figure out how to evaluate this integral, first off, this circle here means you're oriented counterclockwise. That's what that means, this circle here. There's 2 questions you always want to ask yourself. Is F conservative? And is C closed? Is your curve closed? And you can divide this up then into, boxes here. The first thing I want to do is if F is conservative and C is not closed, what can I utilize? Well, that means if F is conservative, I have path independence. That means I can automatically, I don't care about how I get from A to B. I can just get to, I can just worry about what the potential function is at my point B and subtract it from my potential point at my starting point, which is A. And so this is the fundamental theorem of line integrals, which could be calculated then by phi at my end point and phi at my starting point. So if F is conservative and C is not closed, we can use this. If F is conservative and C, if F is not conservative and C is closed, at that point, we know we have a bounded domain, so we can utilize Green's theorem / Stokes theorem. So in 2D, this is Green's theorem. In 3D, we have Stokes. Now, as a reminder here, if F is conservative and C is closed, well, looking at the fundamental theorem of line integrals, the end point and start point are the exact same, right? This means that I have like a number minus that same number, which this means this is 0. That's very nice. And lastly, we have no techniques here. We just have to kind of go brute force if I have no conservative or no, not closed. So I kind of have to use the F of R of T method. F of R of T started with R prime of T. Sorry. Kind of integrating in that way, right? These are all for these types of integrals, all for these types of work integrals. This is always the exact technique that we kind of use. So in this question, F is conservative. We have that. C is closed because it's a circle of radius 2. Right? It's a complete circle of radius 3 centered at this point. And so therefore, the answer to this is 0. Done. That's really nice. No more for that problem. So you saw that C is closed. C is closed, which implies that this is equal to 0. That's kind of what I want to say there. Next thing, part C, we want to find our potential function. So our potential function here, we again note that I have F is equal to grad phi, which means that I have e to the y, x e to the y plus 2y. This is going to be equal to phi sub x and phi sub y. Something like this here. Something like that. I'll at least come over this way. So here, what we notice is I need phi sub x. I need the derivative of this function to be equal to, with x is just e to the y. The derivative of this function with respect to y is x e to the y plus 2y. Now you can use the same exact technique that I just did before up here, where I kind of am searching for my g in the same exact way. It's actually the most common way. It's kind of, I mean, at least the way that you could do it is kind of more down here, where I kind of have this h of z and I'm finding the derivative and kind of working backwards. So in the exact same way I could do this here, but I can also do it in this manner. If you don't like that way, you can also do that. Integrate both of these with respect to x and with respect to y. So the derivative, the integral of this function, which is going to be the potential function now, is going to just be x e to the y. But when I integrate with respect to x, I do have to include my function of y, which could be there. Over here, if I integrate this function with respect to x, I'm sorry, with respect to y, I get back out to my original function as well. And this becomes x e to the y plus y squared plus, well, what do I have to include now? Well, if I integrate with respect to y, this becomes some h of x, some function of x. And now these two functions must be the exact same. Or these functions must be the exact same. So if they are the exact same, we see that they have, well, what is g of y of x? Well, g of y should just be a function over here that's just in terms of y, which is y squared. This h of x, though, is non-existent over here. There's no function just purely of x. And so therefore, our full potential function is really this red part that I've kind of written here. And so therefore, that means that our potential function is equal to x e to the y plus y squared. You don't have to include the k, not matter at all. You can just honestly just let it be 0.
Nick, I have a question before you move on. For when there's only 2 variables, is that when we can set them equal like this, rather than when there's 3, where we would have to kind of solve for the missing parts like the last one we did?
Yeah, so you could do the same method as last time for this problem. You could definitely do that. I actually personally like that method a little bit more. But in this case, it's a little bit easier to visually see it. In the above one, it's very, 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 very difficult to kind of see what's missing from each.
Okay.
And so because of that, that technique will be a fail-safe way of doing it. In this case, it's a lot easier to visualize what's g of y, what's h of x.
Yeah. Okay. Thank you.
Yep, no problem. So D here notices that I am trying to evaluate this same integral again, where C is the portion of the ellipse x squared over 4 plus y squared over 9 equals 1 from 2, 0 to 0, 3. Okay. So, you know, this curve, if I was trying to, you know, parameterize this, right, kind of work with that, parameterizing this curve is going to be very difficult. An ellipse is not too easy to do. I could do it. It would be like 2 cosine of theta, 3 sine of theta. But again, I don't want to really deal with that, especially with e to the y. I'm going to have e to the cosine. Kind of disgusting. So I notice here that I have a conservative vector field. I don't have a closed curve, but I am going from 2, 0 to 3. So I'm going up like maybe in this direction here. And I notice that this is actually a conservative vector field. So because it's conservative and my curve is not closed, I can utilize the fundamental theorem of line integral, which means that this integral then is just the evaluation of this potential function at my end point and my potential function at my starting point, and just subtracting them. In this case, my end point here is 0, 3, and my starting point is 2, 0. And now we just plug it in. So I plug this in, I plug these 2 points into here. We would get 0 plus 3 squared minus 2 e to the 0 plus 0, which is just going to be equal to 7. And that's my answer. So kind of nicely putting it here, the processes for these problems are basically the same, and it always kind of follows, you know, making sure that you kind of know what technique to use, kind of using the conservativity or the closedness of my domain here. Yeah. So this square right here is only for this integral. It is only for the work integral. There's for no other type of integral here. This will not work for anything. We've only tackled this type of integral, at least the different processes. So this will only work whenever you see something of this form, or you see something of this form, TDX plus TDY, because these are the equivalent. These are equivalent here. So other than that, you can't use this kind of technique. Any questions here that I'm missing? At least on this question, anybody has any other problems there? Okay. So then I am going to fall of 2018 problem 2. Sure, we could do that. Let's review ourselves a little bit more about the gradient. There, do that here. So this is fall 2018, problem number 2. Ooh, I cannot see that what I'm doing. Very important. So fall 2018 number 2. I have f of xy is equal to x squared plus y to the third. So I'm just going to go through all the problems. I know that this person asked to just do C to the E, but I need to kind of do A and B as is. So I'm just going to kind of go through it. Just going to kind of remember it. The first one is to compute the gradient of F, which is not too bad here. We just compute the derivative with respect to x, which is 2x. The derivative with respect to y is 3y squared. That's our gradient. Then we calculate du of f. We calculate this guy at the point 1, 2, in the direction of u, 1 over the square root of 2, negative 1 over the square root of 2. Like that. So the first thing to realize is, what does this mean, right? This is the directional derivative in the direction of our unit vector u. So this first off, and the important thing to realize here is I always need a unit vector. So this gets you how fast the function is moving, how fast my height is changing if I move in the u direction. If I move in this direction, which is like in the negative 45-degree direction. If I move in that direction, how fast is my height changing? We can calculate this with the gradient of f dotted with my unit vector. This must be a unit vector. You should always, always, always check if your unit vector you're given is in fact a unit vector. In this case, we can actually check that it is. So the magnitude of u here is just the square of this guy, which is 1/2, plus the square of this guy, which is 1/2, plus the square root of 1, which is 1. So we're all good. We now calculate the gradient of f at the point 1, 2. And doing this would just be 2 and 12. And so therefore the directional derivative in the direction of u here at the point 1, 2 is going to be equal to 2, 12, dot product with 1 over the square root of 2, negative 1 over the square root of 2, which is just equal to 2 over square root of 2 minus 12 over the square root of 2, which is negative 10 over the square root of 2. That means I'm decreasing in height at a rate of 10 over the square root of 2. If you're asked to interpret, that's kind of how you would interpret. Okay, now the next part here, I'm going to kind of zoom out a little bit. Next part here, this part C, here is asking specifically what direction is f increasing most rapidly at? At 1, 2. Well, as a reminder, the direction of fastest increase is always the gradient. The gradient gives you the fastest increase. The gradient of f is the direction of fastest increase. And we can see that from the definition of the dot product here by playing around with it and manipulating, trying to figure out what cosine of theta is biggest. You might have remembered that from what maybe DJ or Mo kind of did it back in the day. So what we do is the gradient of f at 1, 2 is, as we calculated, was 212. And that's my answer for D, for C. I don't need to make a unit vector. It's not necessary at all. I can kind of do that. If you're asked for the direction of maximum decrease, if you're asked to do decrease, the direction is just negative gradient at 1, 2, which would just be negative 2, negative 12. It's the exact opposite direction. So think about it this way, right? If you're on the mountain, I'm going up the fastest way. I'm going up if I'm going up in the fastest slope, right? If I'm trying to do that, I'm going to just, if I want to go back down the exact opposite way, it will be the fastest decrease. So it'll just be right back in that way. D here, the max rate of increase. It's just the magnitude of the gradient. And so the magnitude of the gradient here is just equal to the square root of 2 squared plus 12 squared, which is the square root of 148. If you were asked for the max rate of decrease, it would be negative square root of 148. It's the exact opposite way, right? Just a negative of the magnitude of the gradient. And lastly, here we are asked to find a normal vector for my surface, which is x squared plus y to the third minus z to the fifth is equal to 10. At x, y, z is equal to 1, 2, negative 1. If I give you a surface of this form, to find my tangent plane or something like that, right, I would find my normal vector. My normal vector is going to be the gradient of a three-dimensional surface like that. So I'll calculate the gradient of f, which is in this case fx, fy, and fc. And doing this here, we get 2x, 3y squared, and negative 5z to the fourth, like that. And so therefore, if I want to find the normal vector, like my normal vector here, all I do is I plug in my normal vector at the point at 1, 2, 1, which is going to be 2, 12, and then -1 here would make this -5. That's kind of my answer. So as a couple of really key remarks there, what I'm going to do here is I note that the fastest direction is always the gradient. The fastest direction of increase is always the gradient. The fastest direction of decrease is the exact opposite direction of the gradient. The max rate of increase is always going to be that guy. The magnitude of your gradient, fastest rate of decrease, it can just be the negative magnitude of that. And then from there, right, if I want to compute the normal vector to a surface with three variables like this, I compute just the gradient of that. And that becomes my normal vector. And I could use this for a tangent plane, for instance. I think that's it for that problem. Does anybody have any questions about that? Okay. So then I'm trying to see, going through some other problems here. Give me a second to try to find what's helpful here. I have been asked to do, in the same exact exam, 3B. So I'm going to do that. So in fall 2018 here, I'm going to do problem 3B, which is going to be, I want to identify and sketch the surface that can be represented in cylindrical coordinates with r equal to 2 sine of theta. Sine of theta, where z is between 0 and 1. Okay. So, you know, this problem here is kind of interesting. So harkening back to a lot of the stuff that we've talked about in the past. You know, how do we change things to cylindrical coordinates? How do we not? And what we can kind of notice here is the first thing is I have r equals 2 sine of theta. Now, in order to change this back to Cartesian, this is very tough for me to see what this is, right? It's very difficult. So what I can do is I could change this to Cartesian coordinates. Now, how would I go about doing that? First thing to remind yourself of is r squared is equal to x squared plus y squared. Right? As well, we have that x is equal to r cosine of theta, and y is equal to r sine of theta, like this. So what we could do actually is, if I want to replace these with you know, x's and y's here, kind of work with that. This is at least my opinion on how to do it. Adina did it a different way, but I think you can get it either way in this case. I want to replace r. I know that r then is equal to the square root of x squared plus y squared. That's nice. But here, I also note that y is equal to r sine of theta. Just like that. So realistically, I do have that I could rewrite this as y over r is equal to sine of theta. So I guess there's two ways you can kind of think about it. This becomes r. If I replace this, if I replace sine of theta with y over r, this will become r squared is equal to 2y. And then r squared here is x squared plus y squared. More formally, I can move this around. And now what I want to do here is I want to manipulate this by completing the square. I divide this 2 here by 2, add 1, because I want to complete the square, but I want to get this in some form of maybe a circle. And so what I see here is this becomes a plus 1, would allow me to complete the square. Right, because I divide this by 2 and square it, so it'll be a -1 squared, which is 1. And so therefore, I would get x squared plus y minus 1 squared is equal to 1. And I have that z is between 0 and 1. So this is actually here a cylinder centered at 0, 1 on my in my xy plane sense, and only between 0 and 1. You kind of think about that, right? I'm going to be x, y, and z here. I want to be at this point. I have a cylinder like that. And that's at 1 here, kind of like that guy, which is a cylinder centered at that point right there. That's kind of that process. Does that make sense to everybody? Anybody have any questions about that? Here? Okay. I have then been asked to do problem 5 on this exact exam, which is a Lagrange multiplier question. So I'm going to do that here. So we have a Lagrange multiplier question, which is again fall of 2018. Number 5 here, which is going to be this following problem, which I would like to find the max and minimum values of f of x, y, equal to 3x plus y, subject to the constraint here. I have g of x, y is equal to 0, or more formally, x squared plus y squared minus 10 is equal to 0. So let's kind of review the idea of Lagrange multiplying methods and why we have this. I guess the first thing to realize here is, right, what is the point of like having this constraint, right? If I ignored this, right? If I ignored this, and I told you find the max and minimum values of this function, you'd go, well, what does that even make sense? I mean, I can go to infinite or I can go to negative infinity, right? It would make no sense. So that's why we always have to put constraints on it. So saying, what's the maximum and minimum values of this, subject to saying this part here, where I have this function. So you could have considered I'm on a circle of radius 10. Oh, sorry, square root of 10. I'm on this circle here, a radius squared of 10. And I have all these points, and I want to know on these points, what is the highest value here? And the technique always is as follows. I feel like I'm freaking a SpongeBob and Patrick, like technique, going back in that way. So what we have to kind of do there, the technique is as follows. We want to find where f, the gradients of f and g, we want to find where the gradient of f and the gradient of g are parallel. And if we're able to do that, finding where the gradient of f and gradient of g are parallel, this will give us an idea of where the maximums and minimums can occur. So the Lagrange multiplying method always, I can't say always, most of the time all the times in our problems, but sometimes it fails in some very, very weird examples. But it will always give us all the possibilities of the extreme values. And so in order to do this, which means that we want to find where the gradient of f is equal to some scalar multiple, because parallel means some scalar multiple, is the gradient of g, like that. Oh, subject to my constraint here, which is usually g of x, y is equal to k. And so we want to find all the values of x and y and z possibly and lambda, such that this satisfies these a couple of equations. Now you never need to solve for lambda. It's not necessary. Sometimes it can be helpful. Honestly, it's sometimes helpful, sometimes not. It really depends on the type of problem. And there's no really given techniques to kind of solve this, at least the systems of equations. Solving systems of equations is a very complicated process and one that I still work on my research a lot, and there's no real nice ways a lot of times to solve these. So in this question, let's kind of solve this. So the first thing you do is complete the gradient of both the constraint and the function itself. So the gradient is equal to 3, in this case, it's just equal to 3, 1. The gradient of g is going to be equal to, in this case, just 2x and 2y. And so therefore, kind of adding these together, putting these together, we want to find where 3, 1 is equal to lambda times 2x, 2y. So we need to get the x coordinates to be equivalent. We need the y coordinates to be equivalent. So we get 3 is equal to 2 lambda x. 1 is equal to 2 lambda y. And we have our constraint, which is x squared plus y squared is equal to 10. I want to be able to find all the x and y's here that satisfy them. Okay. So what kind of techniques can we use here? Well, in this part, you know what? One thing I always like to do honestly, is to figure out maybe is there a way to get things by themselves, right? Get things, together here. The first thing to note, I think, is that one way you can do this, that's my opinion, is you can solve for lambda on both sides in this case. So you can kind of manipulate this to get lambda by itself. Now, the thing becomes a little bit weird when I want to divide over. So what does that mean? If I want to divide over like 3 over x, for instance, 3 over x here is equal to 2 lambda. I only can do this when x is non-zero, right? I only can do this when x is non-zero. If x is 0, this causes some issues. Right? This will cause some issues. And so in this case here, for both of these, if x is 0 though, let's find out if x is 0, what would happen? Well, we wouldn't gain much insight, at least here. But in this case, x can't be 0, right? Right? X can't be 0, because if x is 0, this doesn't get satisfied already, right? Because 0 is equal to 3. So we can divide out by x, and we'll find, because x cannot be 0 off of that. Similarly with y. If y is 0, this would not be satisfied here either. So we're able to divide out by x, or divide out by y. We should always check that first. If x can be 0, if y can be 0. If not, we kind of work from there. In this case, we would get that 1 over y is equal to 2 lambda. You get that. And so because these are two of the same exact equations, we can get them that 3 equals x equals 1 over y. This is to be equivalent. Or more specifically, this means that x is equal to 3y. Like that. Now, from these two equations, we get that x has to be equal to 3y, but we have to have one more condition, right? I need to solve for x or solve for y. I have this last condition here, which is I'll call this equation 3. And so what I'm going to do now is I'm going to plug in my equation, x equals 3y. I'm going to plug it into here. So wherever I see x, I'm going to plug in 3y, which will become 3y squared plus y squared is equal to 10. I'll get 9y squared plus y squared is equal to 10. And then for 10y squared is equal to 10, or more succinctly, y squared is equal to 1, which means that y is equal to plus or minus 1 here. Those are my possibilities. So now I get that y has to be plus or minus 1, and I can get what, in this case, I can go put this back in to x here, into my y here, and get what the x coordinate has to be. So in this case, when y is equal to 1, I will get that x is equal to 3. So I have a point 3, 1. When y is equal to negative 1, this means that x is equal to negative 3, which means that I get negative 3, negative 1. So these are the 2 points that I can have extremes on here. That's a good question that you asked there, Nikki. Yeah, so we always assume, and this is actually an interesting point, we always assume that lambda can't be 0. So you could divide out by lambda. That would be fine. You could divide out by lambda and go from there if you would want to, honestly. So for instance, you could have done something like this, where 1 over 2 lambda is equal to x over 3. And similarly over here, you could have gone like 1 over 2 lambda is equal to y. Like that. So we always assume, because think about what would happen. What would happen if this kind of bonkersly went awry, right? If lambda is 0, these wouldn't be parallel. It wouldn't make sense to kind of think about it that way. Like, because this would be the 0 vector, and this would have to be then the 0 vector, right? So again, we want to think about that parallel. So we usually assume that lambda is non-zero, so we can divide by it. You're absolutely right. We could do it this way. Yeah. So we get these two here. Yeah, no problem. So we get these 2 parts here. The last thing we do for the Lagrange multiplier method is we now take all the points we've collected from the possible points that are extreme, and we plug them back into our extreme. We plug them back into our function that we want to see what the max and min are. So what we do now is we take these 2 points, and I want to calculate f of 3, 1 and f of negative 3, 1. Negative 3, negative 1. And I hope you'd agree that this kind of, satisfies it. It's really nice. It's 3 times 3 plus 1. 3 times 3 plus 1, which is 10. And then we have 3 times negative 3 minus 1, which is negative 10. So if we are asked here specifically, make a chart showing your solutions, sure, we can make a chart. Max and min. So F is equal to 10, and this occurs at the point 3, 1. So their max value is 10. Okay, that's what that means. Your maximum value is 10, and it occurs at the point 3, 1. Your minimum value is negative 10, and this occurs at negative 3, negative 1. And this is your answer. If you had more than one value here, if you had more than 2 values here, if you had more than 2 values here, you would have to kind of go through and make sure. Most of the time when you get more than 2 values, there can be multiples of the same max or min, which is okay. Sometimes you'll get a Lagrange multiplier that it doesn't make sense actually, where the extreme value for one of them is just less than the others, which is okay. It just happens there. The chart here is really vague, so you never have to include the lambda. You never have to include the lambda. That's actually called the Lagrange multiplier. A lambda you can find out, they mean something really interesting. They're called eigenvalues for a reason. They're related to matrices, and they actually talk about the direction, kind of the slope through the point, kind of the slope that you kind of that the gradient kind of goes in some way, and kind of the multiplication of it. It's kind of a weird way of thinking about it, but regardless, there. That's that. Yeah, does anybody have any questions about that?
When you have the system of equations like 3 equals 2 lambda x, if you had like 3x equals 2 lambda x and then you tried to divide it and the x is canceled out, like how could you tell if that was okay?
So that's not okay usually. So the way you would check that then, if you have something like, there is a, like you're saying, like if I had 3x equals to 2 lambda x and like y is equal to 2 lambda y, something like this.
Yeah.
Here. So what I would suggest doing instead here is not dividing out by x, but actually moving everything over to one side and factoring.
Okay.
So you would get 3x minus 2 lambda x equals 0, and then you would factor out an x. And so x equals 0 could possibly be it, right? And then from there, you would have to kind of check the other conditions to see if anything breaks from that point.
Okay.
Does that make sense?
Yeah, thank you.
Yeah, no problem. So for instance, if you had this exact system, for instance, x equals 0 wouldn't break this because x equals 0 would satisfy, well, it doesn't matter because x is not in here, but it would satisfy this one because you would get y squared equal to 10. So you get y is equal to plus or minus the square root of 10. And that would be your critical point there. Yeah.
Okay.
Yeah, so that could be something like that. But then you would have your other one, which would be lambda equal to 2/3. And then you could find out what y would have to be and go from there. Yeah.
Okay, thank you.
Yeah, no problem. Any other questions here? Okay. So I am trying to see what other parts we're missing here. Yeah, so I want to at least tackle, so I only have about 20 more minutes or so here. I'm going to try to get through as many of these questions that people are asking as possible. The first one I want to at least say here, let me at least kind of just see really quickly. Yeah, so let me at least talk about ways to find tangent planes very quickly. And all of that here. So we didn't cover a lot about normal planes and stuff. Oh, excuse me. On normal lines and planes. So there's actually 3 different ways we can calculate tangent planes. Actually, so let me zoom this out here really quickly. So for a plane, we always need a minus x0 plus b times y minus y0. plus c times z minus z0 is equal to 0 here. So if I'm trying to find the equation for this plane, if I just give you this, well, just as a reminder, what do I need? I need a point, which is x0, y0, z0, and I need a normal vector, which is a, b, c. The first way of kind of going about it is if I, the first way, one way we kind of did it was back in like chapter 12 way. Chapter 12 way. Which a lot of times just required me to kind of use some geometry to kind of see what my normal vector would be. The other ways you could do it was maybe take, you can either use geometry. You can maybe use your cross product. Find two vectors on the plane, right? That would be one way I could kind of do that. Maybe think about, intersection, stuff like that. That was kind of a chapter 12 way of finding my normal vector n. Geometry, for instance, would be something like the plane that's perpendicular to this line. Then you would just take that line, you take that direction vector and kind of work backwards, something like that. The second way we kind of did it was if I have a surface of f of x, y, z is equal to a constant k. Something like this, what we found, right? There were a couple, actually there's two kind of methods here where you have, a similar thing where I could do z equals f of x, y also. But these are both the same exact kind of problem. If I have some surface here that's described as z equals f of x, y, and I, or I had something like this, they're the exact same thing because I could actually rewrite this as 0 is equal to f of x, y minus z. I can rewrite that. So these are the exact same idea. So I have a function just of x, y, and z is equal to a constant k. Your normal vector here is just the gradient of f at the point x0, y0, z0, whichever point you're at. That's at least that technique here, where what I do is I calculate the gradient. And that's my normal vector here. The third technique is the one that we kind of learned in chapter 16 here, where what I do is if I have a parameterization of R of u v, y of u v, e of u v, what I do is I remember that the cross product here between RU cross RV is my normal vector. So these are really the three ways that you kind of go about solving for the normal vector for a plane or finding the equation for a plane here. Just in general. So in chapter 12, we kind of use geometry or cross producting, finding two values of the plane. Maybe I have 3 points, right? Making two vectors from them, taking the cross product, stuff like that. Intersections, maybe if you were thinking about, maybe not intersections, just intersections here, I was maybe thinking about like the line between two intersections. You have to take a cross product to find the direction vector. In 2 here, right, we have this full surface, right, in terms of equal to k. In normal vectors, then it's the gradient, because the gradient is orthogonal to level surfaces. So it is orthogonal to any level surface. And lastly here, RU cross RV would give you a normal vector. Okay, so these are the 3 ways you would always try to find it on your plane. I remember, I know this sounds really mean, but it's not. When on my final that I made for my students in the winter, I actually had them compute a tangent plane in 3 different ways, using in 3 different problems completely. One using kind of a cross product kind of thing, one using the gradient, and one using this RU cross RV kind of method. I find it really, really important that you know all 3 of these ways because they all have a really, really important concept to kind of figure out how to find normal vectors. Normal vectors just in general are really important applications. And lastly here, I guess on top of that, you might be thinking about lines. Lines don't have a lines are a little bit interesting because R of t here, we usually write this as R0 plus t times v, where v is our direction vector. So how would we find those? There's a couple different ways we could find those. The first thing, the normal line, if you hear about the normal line, to a surface, if you had some f of x, y, z is equal to some value k, your normal line would just be the gradient. The vector v is actually just the gradient of f at a point x0, y0, z0. It's a line through the normal vector. And we know that the gradient will give you the normal vector, so it kind of makes sense there. In chapter 12, but we kind of discussed a lot of different ways to do it. You know, from point A to, if I wanted to have a point from, you know, a line through A and B, our direction vector might be something like B minus A, using very bad notation, right? I would kind of do that. Line segment then, if I did this exact thing, would be between 0 and 1, the time domain. As a reminder, right, you have the symmetrical equations too, and the parametric equations. Make sure you kind of remember how to kind of do that, right, to solve it for time, for the parametric equations, to get the symmetrical equation, like that. You might have, this would be maybe the intersection part, where the intersection between two planes. What line is that? Well, that would be the cross product of the normal vectors, right? This would be, you know, your v would be n1 cross n2. That case. Were there any other ways we did it? There are probably some other different ways to do it, but you know, it really will come with the geometry of the question as well.
Nick, for the intersection, what does that say after?
The direction vector is the normal vector of the first plane across the second plane, the normal vector of the second plane.
Okay, thanks.
So it's the cross product of those two, right? If you just look at a wall, you kind of think about that the plane that the line that intersects both two planes has to be orthogonal to the normal vectors of the two planes itself. So, which is really nice. And you also might use geometry at some point, just some parts of the geometry there. The other way you could do it, right, is knowing the slope is related to fx and fy. Right, as a reminder there, fx is the slope where you know, y is constant. X and y is when x is constant. Right, so those are important to kind of remember there. I'm kind of working through that in some form of a line. If you hear the word tangent line, what's the slope of the tangent line there? You just do fx if it's constant. Or the slope of the tangent line in a certain direction, that could honestly be du of f, right? That could honestly be just the direction of that is also the idea of the slope of a tangent line there, in that direction of u. Okay. Am I missing anything? I don't think. Yeah.
I just have a question. For the like plane stuff on the left side and then the line stuff on the right side, why is the gradient of f x y z for both? Like, why is that equal to n and equal to v?
So good question. So this is the normal vector to a plane. Right? This is a normal. This is always the normal vector to a surface. The normal line, if you're asked to compute the normal line is the line that goes through the normal vector of a surface.
Oh, okay.
Yeah. So yeah. Sorry if I didn't make that clear. I apologize. So the goal there is, right. That's all I'm doing. I'm actually calculating the normal vector in that case that way. We also have the normal vector too, right? In some way, we also have, I just realized this, right? We also have the unit normal vector, which is equal to the tangent vector, the derivative of the tangent vector divided by the magnitude of the derivative of the tangent vector. It's another way you might be able to calculate that or use that somehow. Kind of like that. Yeah. Does that make sense to those of you who asked that? Lauren, does that make sense here?
Yeah, thank you.
Yeah, no problem. Okay. So I'm gonna see. Yeah. So I'm gonna do, I think, probably one more question here that people are asking for, which is I'll do fall 2018, number 10. If nobody has any other questions about the lines and planes here, I think that's good. In that case, kind of think about here. So another divergence theorem question here, but kind of a little bit different to make sure we get our bounds, our ducks in a row here of bounds. Kind of like that. So I'm not going to write that for everything. So I have my vector field, which is z, y, x, kind of like that. And in this case, I want to find basically where my surface S is the surface of the tetrahedron of x, sorry, 6x. 6x plus 3y plus z is equal to 6. At x equal to 0, y equals 0, and z equal to 0. So it's just a tetrahedron in the first quadrant. And we can always draw this tetrahedron. It's always really important to draw this tetrahedron. So how do we do this, right? I want to basically find my x, y, and z intercepts here. So if I want to find my x-intercept is when y and z are 0, right? That's on my line there. So I would get that this is 6x is equal to 6 and x is equal to 1. So I would get 1 here. For y, we would get that this is just 3y is equal to 6. And so y is equal to 2. And lastly, for z, this is when z is equal to 6, right? When x and y are 0. 2. And so this is it. So we can kind of draw this tetrahedron here. So like that. And my surface is actually all parts of it. And it's completely bounded. Now think about how complicated of a question this would be if I did not have the divergence theorem. I would have to calculate the flux. I'm trying to calculate the flux. I'm trying to calculate this guy here, specifically this, across this surface for 4 different parts. So I would need to do 4 different integrals and add them all up, compute all the fluxes and add them up. But because I have a completely bounded domain here, I could switch this over to just computing the divergence theorem of this and using the divergence theorem. So this could be then equal to the triple integral over E of the divergence of F dv here, because I'm completely bounded. Now, with this in mind, we then compute the divergence of F. So let me compute the divergence of F here. Computing this is actually really nice because I take the derivative of this with respect to x, this with respect to y, this with respect to z, and add them up. This is going to be 0 plus 1 plus 0, which is just 1. That's very helpful. So this actually just becomes, this is silly, but this also could just be the volume of my domain E, of my volume E, because this is a 1. Now I can't really come up with a nice formula for the volume of a tetrahedron. There is one, I just don't want to memorize it. So we can come up with the bounds for this. The way you can come up with the bounds for this, kind of thinking about a triple integral here, is, you know, you can go any way first. I usually like to think about this if I have a tetrahedron, go with respect to, you know, z first here. So we kind of draw lines going upwards, like this. We kind of lines going up this way. And where do I always enter the region from, right? Where do I always enter and where do I always exit the region from? Well, I'm always entering the region from the xy plane. I'm always entering there. And I'm exiting the region from the plane itself. So the plane would be below by 0. And the plane here, I can rewrite this as 6 minus 6x minus 3y is equal to z. And that's how I can kind of write this. So my domain would be 6 minus 3x minus 3y. Sorry, I'm sorry, 6 minus x minus 3y. Like that. Okay, so that's that guy. Then what I could do is I could realize here that what I need to do then, since I've kind of done this, I need to project this surface down onto the xy plane after I've integrated out z. XY plane here. This is a 2. This is a 1, and I can come up with this kind of little triangle right here. Oh, sorry, this is the 6x still. I'm sorry, I'm not writing that correctly. I was like, what's happening? Sorry, that was making no sense to me. Sorry. There we go. And what I want to do then here is to now try to come up with the bounds for this little triangle here. And I note that this is actually equal to, this line right here is when z is 0. So it's actually equal to 6x plus 3y equals 6, this line. So 6x plus 3y is equal to 6. If I just divide everything out by 3, this becomes y is equal to 2 minus 2x. So this line is y equals 2 minus 2x here. So I could do this with respect to y first, kind of integrating that with respect to y. Doing that, I would enter at y equal to 0, and I would exit at the line 2 minus 2y. So my y here would be between 0 and 2 minus 2x here, sorry, 2 minus 2x. And then my x bounds would just be between 0 and 1, right? I would have this just be a constant as always. I end with that. And these are my bounds. Sorry, I missed this guy. Yep, those are my bounds. And so therefore, this would just be the triple integral from 0 to 6 minus 6x minus 3y, 0 to 2 minus 2x, and 0 to 1 of a 1 in here and d z dy dx. And just integrating that guy would give me my answer here, evaluating this integral down here. Yeah. So that's kind of the process there. Does anybody have any questions about that? That I can answer? Does that make sense how we kind of went through that?
So it doesn't matter which variable you started with. Like you could have done solve for like you could have did dy dz dx or dy dx dz.
You could do any of those, yeah. In this case, it could be written as really any type 1, 2, or 3 integral. It doesn't really matter what you do first. You'll get the same exact thing, but when I integrate with respect to the first variable, I then project onto the plane of the other two. So if I integrated first with respect to x, then I would project onto the yz plane and figure out my bounds from there, like that.
You can give a minute to go over like type 1 versus type 2.
I mean, the type 1, type 2 is I mean, you don't have to know you don't have to know type 1, type 2, type 3. It doesn't really matter what the number. Yeah, it doesn't really matter that way. It just matters like if I integrate with respect to x first, I would then have to project onto the yz plane. If I integrated with respect to y first, I would just have to project with the xz plane. You don't have to know the names of type 1, type 2, and type 3. That's not a problem.
Okay.
Yeah. And somebody has asked a question. You should jump to it. So the only time you could do this to jump to the divergence theorem here is making sure you have to do two things. One, to make sure that they're including all four parts of the tetrahedron. And secondly, that it's a flux integral. If I'm just calculating the volume of a tetrahedron or something like that, or some other integral, if I just calculate something like this over the tetrahedron, it would make no sense for me to use the divergence theorem, right? So I always want to just make sure that I'm computing the flux integral. If so, and you have included everything there, yeah, just go ahead and go straight to the divergence theorem because of that. Because I have a completely bounded domain. Yeah. Any questions? Yes.
Will it always be in that sort of form? Meaning like we're going to be doing the triple integral of like 1, or are we going to have something inside of that?
You might definitely have something inside of it.
All right.
Yep, that's definitely reasonable. This is not too hard of an integral, thankfully. If I had put something else in there, maybe like a y or something, it wouldn't complicate things too much.
All
Yeah,
right.
yeah. But you have to kind of think about that you know, these integrals won't take too long to integrate overall, because again, there's a lot of questions on these exams, so they have to kind of make these integrals at least somewhat reasonable. If there's a lot of weird stuff in here, you might go, did I do something wrong? Or should I be integrating this a different way? Maybe I should be integrating this maybe with cylindrical coordinates or something like that.
Okay.
Yeah. Any other questions about this problem?
Could you just state the conditions for the divergence theorem one more time?
S has to be completely enclosing a volume E. Okay, has to be completely enclosing a volume E. I need my surface to be completely enclosed. I need all of the surface that is completely enclosed. As well, we need to have an outward normal vector. An outward normal vector, in this problem, we actually, did it say that we have an outward normal vector? It actually didn't even do that. So it's whatever. Well, usually I have to assume that it's not, but it's okay. It's not there. Dude, honestly, there's not too many. If I just have an outward normal vector for all parts, and I have a completely enclosed domain, I can use it if everything's continuous and all that stuff. Yeah, those are really the two conditions. I have to be completely bounded those. I cannot do this with just a regular surface. It has to completely encapsulate a volume. Yeah, that's the main point. And we have to be computing this type of integral. Okay, so it is 7 o'clock here. I'm at least gonna, I think I'm gonna start to head out here. Yeah, so I guess, thank you for the people that stayed for the entire time. Thank you for staying all the time here, and made me kind of go a little bit delusional here at the end. I hope you guys do well tomorrow. I think you guys will do great. Regardless, thank you guys for coming. If you have any other questions or want to email me or anything like that, feel free to do that. I'm only going to be awake till 8:30 or 9 tonight. I will. I go to bed a little bit early. We usually wake up around 5 or 5:30. So, yeah. But I will see you. I'll see some of you tomorrow, I guess, and all that. So I hope you guys do well. Other than that, I hope you guys continue to do well in your other exams and your other papers that you have coming up. I know it's a really, really stressful time, and hopefully this whole thing, you know, however long this thing lasts, I hope you guys will enjoy your summer in some capacity. Yeah. So our proctor info, you're not going to be told who your proctor is until you get there specifically. So I don't know. I only know my students. I don't know anybody else's students. Point. So I actually don't even know who's proctoring who on this point. So yeah. If you have any questions, let me know. I hope you guys are doing well. I'll stick around for a little bit if you guys have any just general questions. But yeah, thanks for staying. And
Thank you.
Yeah, no problem.
Thank you.
Thank you.
No problem.
Thanks, Nick.
No problem.
Thank you very much.
Anytime.
Thank you.
No problem.